the first workshop on mechanistic interpretability. Thank you all for being here. And yeah, it's a great pleasure to be here with all of you. And, oops, sorry. Yeah, my name is Fazil Barres. I'm one of the organizers. And I'm going to quickly run through our schedule for today. So this is the overall schedule for today. You should be able to see your slots if you're speaking on the website. So we'll start with David Bau's talk, and then we have some oral presentation spotlights, poster session 1. So you'll get some indication of where we are. Then there will be a panel discussion and lunch, and then we'll continue in the afternoon. So I really don't know much about the rules. I've tried to figure out what the rules are here, but the only thing I managed to figure out is if there is a fire, please use this door and get out of this room. No one really knows anything else here. So
please do not die.
Thank you. That was implied.
There is a fire. Yeah. Yeah. There's a sign on the other end. No entry or exit.
Great. This event was sponsored by a Beneficial AI Foundation and AISTOF. So they have helped us with some of the merch we have here, which you should be able to pick one by lunchtime. And we also have a very nice social plus dinner and drinks after the workshop. So if you haven't registered, please register for that. Of course, as most of these events go, we would not be able to be here if it wasn't for our team of reviewers. And special thanks go to Hoagie, Tom, Sam, Sheng, Alex, Eric, Tom, Arthur, Vikrant, Alexander, Johan, Lovis, and Nevin. So thank you all for helping us review all the great papers that we have in this workshop. As I mentioned, here is the QR code for the evening social. If you haven't applied yet, we encourage you to apply. We do still have some spots left. And Neil has kindly created a channel in the open source MacInterp Slack where we'll communicate future events or anything that might come as a result of this. So please scan this QR code if you want to know about future events. And of course, I might be standing here doing the talking, but it goes without saying that this event would have not been possible without my great co-organizers. So please join me in putting your hands for them. Thank you all. More couldn't be with us here today, unfortunately, but I'm hoping that you'll get to meet Kayo later on. And oops. So a few other thoughts that I didn't mention already. So the point of these poster sessions are for you to go and ask as many questions. There are no such thing as dumb questions, even if you haven't read the questions before. So try to engage as much as you want. We also know that today is going to be a very long day, and the whole point of bringing you all here together is to meet one another and to build connection and form collaboration. So at any point you feel like you want to talk to someone, feel free to step outside and talk to them and build those connections. So no offense taken, at least from my side, if you decide to use your time otherwise.
There's a lot of content, and we are not expecting people to be at everything.
That's right. So with that, I would like to invite our first speaker, David Bau, who probably doesn't need any introduction in most communities, but David is very well known for his work on MacInterp, and he's going to tell us a lot of exciting stuff that he's doing now. So please welcome David.
Well, we have some technical issues right now. Apologies for this. How do I... All right, there we go. And this should just work.
please.
Okay. Yep. That's good. That's great. Great. Perfect. Not sure about this title, The Fundamental Duality. Wasn't sure if I should keep this title, but I'm going to try to make the point that interpretability is pretty central to machine learning. So that's a grandiose title. And so, what is it that we are after here in this room, in this little growing subfield of ours? Right? It's pretty simple, right? Most of machine learning practice is about asking this question: what an AI system can do. But we ask a slightly different question. We shift this. We ask, how does it do it? Why does it do it? So we're like, that's sort of our responsibility in this community to ask that question, how? And so let me frame this a little bit. So what is our job as a field, and how are we doing at this? How long have we been at it? Let me sort of open this up as a question. I'm going to make the case, interpretability research is foundational to deep nets. So when did deep net researchers start doing mechanistic interpretability research? Like, what can you think of as like the earliest paper in this area? Like, what year would you say? Oh, I'd love to. Oh, throw out a year. Oh, 2024. No. What year? What? 2014 maybe. 2013. Yeah. So there was actually a fantastic paper in 2014. I think Matt Zeiler wrote this great paper called "Visualizing and Understanding Deep Nets" that was very influential to me. There was some other work that was going on around that area. I think that the people who came out with Lime asked this question: can we trust a deep network? That was very influential. So you could consider that mechanistic interpretability work. I looked through the literature. Let me put the year up that I found when people started looking at this. Look at that year, 1986. Do you guys recognize this paper? You know which paper this is? Learning representation by backprop. This is the backprop paper. This is the paper that Hinton won the Turing Award for, right? Is this an I thought this was a paper about gradient descent. Well, I recommend going back to nature and opening up that paper. And yes, you see a few equations for gradient descent there. But the truth is, gradient descent, that's Newton stuff, right? Hinton doesn't really lay claim to gradient descent. What he lays claim to is these figures. Look at all this. These are the figures in the paper. What are these figures? These are mechanistic interpretability studies. What he does is he says, hey, let's try training deep networks. Let's stack up more than a couple layers of neurons. We'll use the simplest optimization procedure we can come up with, gradient descent. And then he asks, does it do anything reasonable? And the way he does it is he looks at the actual weights. He looks at the actual activations. He convinces himself that there's reasonable representations going on here. Like, this is him taking a look at a network trained to detect symmetry in these symmetric pixels. And he looks at every single weight of this network, and he realizes, the weights are organized in this anti-symmetric way. I can understand the algorithm that it's implementing in order to detect and classify a symmetric row of pixels. It's very sensible. There's this exponential backoff in the weights, and it's anti-symmetric, and then there's this, this balanced thing that comes out to the last layer to actually classify. Why was he doing this? Well, because he was after generalization, right? So there's a fundamental duality that really underlies all of this work that Hinton has embarked us on as a field since 1986, which is that there's this hypothesized duality that underlies the whole idea of deep networks, which is that generalization, which is what we've all been after in machine learning forever, right? Generalization arises from computational reuse. So there's this like duality between generalization and reused computations. That's his intuition. And so he says, therefore, when you have deep networks, you should stack them up in layers. if you have multiple layers, that allows the early layer computations to be reused by the later layers that they call these hierarchical feature representations and so on. It's a form of reuse, and the intuition that drives Hinton's desire to make these networks deeper is that when you have computational reuse, it should allow the network to learn computations that it can reuse in different situations, in different places. And then in traditional computer science, we call reuse modularity. If you program a modular program, then it should generalize better, right? And so it should learn faster, it should generalize better to new situations. So that was the dream back in 1986. And the truth is, I don't think that he really believed in it as deeply as it actually is true. Because it took many years for people to be bold enough to push these networks to the size and scale where we can see them seeming to work for complex reasoning now. And so the problem that's really in front of us now is how is this whole hypothesis working out? Does this actually work in complex reasoning? And now what we've done now today is the way we test for generalization, the way we've done it in the intervening decades, is we tend to test generalization in an easier way than Hinton did in this very first paper. We tend to test it by testing a holdout set. But we're sort of at this interesting time when holdout sets are starting to fail us for a couple reasons. One is we're starting to train networks on all the information that humanity has ever produced in the history of mankind. And it's a little bit awkward to try to contemplate what holding out a little bit of data from all the world's information is. And then the other reason is that we're really getting amazing types of generalization from these models where we're pushing them to generalize out of domain all the time. When you recommend to your friend, use ChatGPT 4, you don't say, oh, and be careful to ask it questions that showed up in MMLU or stay in domain. Like you don't do that. You say, no, be creative, ask it something new, do something new. So we're constantly pushing these things out of domain, and that's the situation where traditional machine learning tends to fail us. It doesn't tell us very much about what the behavior of these networks is when you test it outside of what you've benchmarked it on. And so interpretability is one of the main attacks on both of these problems. And so the question in front of us is, can we actually explain some of the higher level generalizations that these models are doing? So one of the amazing things from the GPT-3 era is the emergence of meta-learning. Who here knows what meta-learning means? Right? So meta-learning basically means learning to learn. For a while, people thought this would be its own whole area of machine learning that would require new architectures. If you've ever heard of hypernetworks, they're a very cool idea. Maybe a second network that can learn to learn and maybe learn to train another network and so on. And people were coming up with all sorts of very creative ways of learning how to learn. People know how to learn how to learn. But one of the amazing things was that large language models, when they got large enough, learned how to do this naturally using Jeff Ellman's old 1990 formula of just predicting the next word. And so let me give you an example of meta-learning. So this is in-context learning. So here I've given you a situation, 13 to 11 period, 18, 14, 4 period, and so on. And you can see what the last question is here. So this is what we would produce as input to the model, a bunch of lines of text. And then we ask this language model, predict the next word. What comes next here? Can somebody tell me what comes next? Be a good language model here. Yes. Yes, 5. But you see the pattern, right? 5 is the right answer. And any of these big GPT models would have no trouble saying 5 here. And the cool thing is that I could do this differently. Let's take the same kind of inputs this way. Here's another set 13 to 15. Okay, so what do I answer down here this time? Would you say? Oh, the word 5. Wait, hold on. The word 9, N-I-N-E, right? And so that's cool. And so to predict these, the model has to. So this is what meta learning is about, because the model is like learning how to perform this task, but it's learning it without changing any of its parameters. It's learned how to learn, and there's been a lot of controversy about how these networks are able to learn from examples without doing any gradient descent. Some people actually argue that maybe these things are doing virtual gradient descent. They're like running a little virtual machine where they're running gradient descent virtually in their activation space. So what the heck is it actually doing? This is an opportunity for us to go back to Hinton's old game and crack open the models and look at the weights and look at the activations and see what's going on here. So I'm going to review a little bit of work that was done by my student Eric Todd here, and this is the ICL. So meta learning is sometimes call it ICL in context learning. This is the ICL setup, and I don't know if my laser pointer doesn't work on white here. So, but you give it analogies, and then you leave the last analogy unfinished. These are the demonstrations, and then the last thing is the query. And then finally, the model will predict a prediction, and that's sort of the form of the ICL setup that you can test with. And you can set up a lot of different tasks here. Eric tested about 60 different kinds of tasks. These are examples like English to Spanish translation, antonyms, and other things. How do we understand how it is an LLM does something like this? So who here has already read the function vector paper? I'll adjust my speed accordingly. So I'll go through this pretty fast. So here's how the basic experiment is set up. You run your in-context learning. This is a picture of the transformer internals, small, big, common, and then the correct answer is rare here. And the idea is that we want to understand what it is inside the model that's allowing it to do this. So we can do this by setting up a contrastive execution where we're running this model twice, one in a situation where it can do the task, and another like contrastive situation where it cannot do the task and where something is missing in it. And then so here's an example where it can't do the task. I just put other words here: quiet, dry, common. I don't know what goes here. These words have nothing to do with anything, right? Now, what I'm going to do though is I'm going to hypothesize that maybe somewhere up here there's some magic representation that like captures this idea that we're trying to do antonyms. This is the task that's up here on the top. It's doing antonyms, and so what we'll do is we'll test that by watching this output here while we take pieces of the neural signals from the top run and transplant them down to the bottom run. So this is called activation patching, or there's other names for this. And so we'll take the activations from here and we'll move them down here. And then what will happen is most of the time this doesn't do anything, right? But once in a while, when we move just the right thing over, it'll make it so that the probability of saying rare is boosted. It'll behave as if what it's trying to do is do antonyms, even though we didn't demonstrate antonyms here. And so what this would be, if we could do this, this would give us evidence that we found the essence, the gestalt, the something up here that's creating this antonym state and transplanted it down to the bottom without having to have examples here. It would be even better if we put a word down here, like instead of common, we could put, so like one of the confounders here is maybe we're moving down the encoding for the word rare, and since this is about to say rare, this is just going to say rare. So an even better setup is if I put like the word big here, and I transplant something, and it'll actually say small, right? So I didn't put that in the slide because it's a little bit more confusing, but this is the actual setup that we do for the experiment. So we have like a different kind of antonym, and so the word small here is completely unseen. It's not, but the only way it's related to big is it's actually related through this task. And if we boost the probability for small, it means that we found something. And so we do this, we scan over all the things, and here's a scan over all the attention heads in the network, and you can see the ones highlighted in blue are the ones that if you bring them over, it actually boosts the probability of doing this task. And so the funny thing about it is that regardless of which of the 60 tasks you try, it's basically the same attention heads regardless. There's a couple tasks that are a little different, but almost all the tasks use the same set of attention heads, which is kind of crazy. The attention pattern for the heads looks like this. It looks sort of like a voting mechanism. And so what we do is we sum up the information that's brought over by all those attention heads. Those attention heads all pour in vector contributions into the last token representation. So we want to see what are these attention heads adding. So we add up all the attention heads to see what they're adding. And we call that vector, which I've put here in little color, the function vector. This is what the attention heads are bringing over. And the cool thing about the function vector is that if we take this function vector and we transplant it to a new context, it'll make the function execute. So normally if I say the word fast means, it'll say, well, the word fast means quick, right? But if I transplant this function vector over, it'll say the word fast means slow, right? And it'll sort of put this network in opposite mode. So anyway, so this is an example of trying to understand more complex things. So do I only have 5 minutes left? Okay. So I have many, many things I want to talk about. I'm sort of giving you a very slow walk through of function vectors. Let me zoom through this. So function vectors are sort of amazing for a few reasons. You can compose them and you can do other things. And it's an example of what I'd say is like an emerging fundamental dogma in interpretable ML for very large models, which are, concepts. We're getting this emerging belief in the model that concepts are generally encoded in representation vectors. There's some approximation to a truth. But it's a nice working hypothesis, and that knowledge is stored in vector mappings between representation vectors, and reasoning seems to be embodied in the pathways that vectors follow as you flow through a big network like a transformer. Now these are sort of hypotheses. These are not things that we've proven as a community, but you can see the community sort of behaving as if these things are likely to be true. And a lot of the research programs that people are designing are suggestive of this. So that they're cataloging all the concept vectors in all of the vector space, like a map of the world. Here's where the Golden Gate is, right? They're enumerating mappings of all the associated mappings between representation. We're looking for a lot of circuits, right? Oh, we have. We actually have. We started to share notes. We started a little late. We need more time. Okay. Well, I can tell you about another paper here. That's all right. So for example, once you've got these maps of the world, you can do stuff like this. Here's like a map, right? So once you can map the world, and once you can map the world of representation spaces, you could do something like, get your large language model to perform a task, and then try to create a map of how that task lives in this map of the world. So these are all sparse autoencoder features. They came out of one of the SAE works. And what Sam Marks has done here is he's taken a task of reading resumes and telling whether somebody should be hired for a job and map that onto a big circuit, a pathway, a set of pathways that connect a bunch of sparse autoencoders, which are measured using salience methods as the most decisive for this classification task. And then what he does is he looks at these 100 or so features. He has more than what I've put on this slide. And then he says, hey, let's manually look at these. Now that I've got this map, maybe I've even pre-labeled some of these things. I can kill the features that look like they're spurious, that they're not actually relevant to the task. It turns out, and if you do a task like this, like reading resumes, you get a lot of spurious features. The network is like, hey, I can tell the difference between male applicants and female applicants and old ones and young ones, and you might be like, I don't think you should look at that. So you can go to all those features and kill them. And the interesting thing is that if you do it and you do it the right way, then you can actually improve the performance of the classifier, especially when you test it on out-of-domain examples. And so there's an example of a kind of thing that you can do with this agenda. But let me give a piece of caution too, which is that I think it's a little too early to declare victory, that we know exactly what we're doing in the field of interpretability. I'm going to give you a couple puzzles. So here's a puzzle about word sequence concepts. It was a puzzle that was derived by Sheridan. So here's a question. We saw what will be is what this transformer is saying, and she asked, what's stored in this vector H? And she asked it in the following simple sense: does it store the previous word, like what, Like when you're sitting here and you have an encoding of will, does it know that what came before it? And so the way that she answers that is she just trains probes to recover the previous word or the current word from the current hidden state. And so what do people think? Do people think that once you get into the middle layers of the transformer, it knows what the word was before? Not really, kind of. Well, I'll show you what she measured. So so for this word that we're currently working on, the transformer actually knows this to about 80 to 90% accuracy with a probe. So it generally doesn't really forget what you're working on. For the word that came before, it kind of knows. It can kind of predict that previous token to between 5 and 70% depending on what layer you study on. It's a little disappointing. It doesn't really have a clear encoding of what the previous word was. It's okay though. It's not bad, right? So, but now she asks this. She says, well, that's for generic sentences. What if we ask like a really meaningful one? Like what if we said, instead of we saw what will something, right? What if we said like we saw Star Wars, right? We saw Star Wars. We saw Star Wars. So what's the answer here? So who thinks that this is going to look kind of the same or different? And in what way? You would think that now this is meaningful. So when you get to this hidden state, it really knows that star came before. I mean, that's like a meaningful thing. That's what we all expected to see. Let me show you what Sheridan actually found. So here's the actual accuracies. And like star, it was previously around 50%, and now it's down at around 20%. It really doesn't know that star came before. And it doesn't even know that it's working on wars anymore. Like that used to be 90%, and now that's down to like 30%, right? Like there's some serious weird stuff going on here. In ordinary text, the information about what token you're working on and what the previous token is and all this token kind of stuff is very present. But then when you're on meaningful entity text, input information is largely erased. It's erased. There's erasure going on. Concept erasure seems like this very systematic, important process that's happening. And so, we're doing this, we're analyzing these funny systems that don't necessarily work the same way that humans do. I think a lot of our intuitions is as we see more text, we get more ideas and our brains fill up with more concepts. But there are other things that are going on in these models. So for example, information erasure is sort of the inversion of a bunch of these feature analysis things. And surprising structure like this might turn out to be very important. So I feel like one of the messages that I have is that we haven't yet explored the whole space of the set of abstractions that might be important to understand. Concept erasure might be an important one. There are other ones here. An example from one of Nikhil's work is that he's looking at entity tracking, and you would expect if you had a short-term memory like box B contains a cup, you'd have some representation of box and some representation of cup, or maybe their association somewhere. It doesn't work that way. It's neither one's represented. Instead, it's the position of that fact in the text which is represented. It says, the last time I saw the box mentioned or something, it was back here on page 17, and that's what it remembers. It remember to go back and read page 17 next time somebody asks me a question about it, which is kind of a cheat. It's probably not the way that humans do it. Or maybe it is, I don't know. But yes, it's quite interesting, and it's very unexpected. And so I think that the reason that I'm highlighting this is because we have a pretty good map of how to scale our field when we're looking for concepts that have good evidence in the input and concepts that have good evidence in the output. We're developing methods for scaling these things with computational power, right? So that's what all the sparse autoencoder work is about. My suggestion is that you've got other abstractions, erasure, references, functions, different types of abstractions we haven't thought of, understanding of complex reasoning, which may require other types of abstractions that we don't know. And we don't yet know how to scale those with computational power. It seems to demand, if we want to make progress in these things, to scale the human side of the science, just to get more people generating more creative ideas, looking at more of these situations, creating more human insight. I think that one of the lessons from history of science is that the breakthrough ideas come from the unexpected corners, from people bringing a new point of view and a new insight. And the question is, how do we scale the human science? And so I want to mention this last thing before I wrap up, because I think that's another thing that's important for our field to do. A couple days ago, Llama 3 405B came out, released by Meta. It's this great piece of news for interpretability research, because for a long time, if you wanted to study a large state-of-the-art model, you would have to be in one of the big industry labs, because everybody's keeping these models so secret. But the fact that the weights are open means that we can now ask questions about the mechanisms underlying, higher level complex reasoning capabilities that only show up in models of this size. But I've been asking people around who's running this, and kind of nobody is. I've run into a few people who said that they've downloaded it, but they don't know what to do with it now. And the reason is because it takes about 1 terabyte of GPU RAM to run, and most of us don't have that lying around. Or even if we do, we're not sure that we trust ourselves to burn it on this. And so what this project is, this is a project that we're starting. With the NSF here. It's called the National Deep Inference Fabric, and what it is it's a system for executing AI research experiments, the kinds of things that we do in interpretability research. And there's a whole system behind it. I'm going to take a minute here to show you what it looks like. It has this new API called NSIGHT. And the way NSIGHT works is it's a PyTorch extension. It wraps any PyTorch model. It has nice language model wrappers like this. But what it does is, instead of calling a model like a function, it allows you to call a model like a Python context, like this. So you can say, oh, here's my model, trace it, and provide some input. And so that doesn't return right away. It creates this context, and inside the context, you have to say what output you want. So I might go to the output of the whole model itself, and I say save it, and then that becomes the output. That's how I define what the output is. Now, actually, I could go into the model, and I could specify other types of output I want, or other things I want to do. So for example, inside here, I can say, in the model, I want to change what the input to this layer is. I want to take these 3 neurons and set them to 10, and then I want to grab an output from some layer or whatever, and then save this in this thing, and then I can produce this output. What this is, these are 3 neurons that Eric discovered, which cause the network to invert its concepts. So instead of saying the truth is the truth, which is normally what it would say, it now says the truth is the lie, which is amazing. This is an amazing neuroscience experiment. Can you imagine going into 3 neurons of a human brain and turning them on, and then all of a sudden, you start saying the opposite of everything that you meant to say? This is what you can do with Llama with this. And so these 3 neurons are kind of amazing. I'd recommend doing this experiment. And so inside the context, you can write arbitrary code. You can write really complex Python code here if what you want to do. And so the trick is, and here's the trick. This is all normal Python. It's a normal Python extension right now. But the trick is, if you add remote equals true to this setup, then instead of doing this on your own GPU, it's sent off to sweet US government-funded, GPUs, and then it runs this. So it creates this this code here is a computation graph that gets sent over the wire. It's a scientific payload, and your code gets sent to run remotely. And since it's a computation graph, we ensure that it's safe codes, it's safe for cotenancy and everything. So it's shared in inference. It's a new type of inference service, is what it is. It's an inference service that's much more transparent than a commercial service. So that's sort of the architecture diagram of what it looks like. So my final message is, so join us. So this is a new system. It's not completely baked and ready for everybody to slam yet, but we'd like you to join us by proposing an experiment to run on 405B. If you have a really, really good idea, and you're really needy and worthy, and you don't have that GPU, and if you just had a little bit, then you could really make a big difference to science. Then apply by June 30th. It's just a few days from here. Just fill out a few lines on a form. Apply to be a pilot researcher. There's an application form here, and and help us build this shared resource for the community. Thanks. I know I went over a little bit, but I appreciate it, guys. Thanks a lot.
All right. We're probably not going to have time for questions, but thank you so much, David, for an amazing talk. I am really excited about all the work you guys are doing to democratize large model interpretability. And yeah, so we are now going to be moving on to our orals. If the 5 speakers could kind of come up near the stage and line up in order, starting with testing the circuit hypothesis. Who's up first? Be careful of that line. One notice is this room is slightly smaller than the popularity of Mechinterp seems to have become. So if everyone could just like shuffle in on the rows if there's any spare seats, so like as many people could have a seat as possible, that would be fantastic. Yeah. Yep, room at the front. We don't mind. It's fine. You get a front row seat of all the amazing speakers. And yeah, feel free during these talks to like come and put your posters up along the sides or like while you're waiting in the queue. We can use that wall, right, Fazil? Yeah. Amazing. All right, and yeah, so, and yeah, if we run out of space, we'll try to bring some extra boards in. And yeah, so the orals are going to be 10-minute talks. There's 5 of them. Rather than having time for questions, what we're going to do is suggest that if you have questions, you go up to their posters. Most of them are in the morning poster session. One of them's in the afternoon. I can't actually remember which one's which. Do you remember? All right. The last one is in the afternoon poster session. And then you can just chat with the authors about their paper to your heart's content. All right. Who's speaking about hypothesis testing the circuit hypothesis? Amazing. Yeah, take it away. And I'll leave a timer up here for you.
The what?
I'll leave a timer over there telling you how long you have left.
All right. Hello, everybody. I am Ashil, and I am going to talk about the circuit hypothesis in LLMs. So first, let me just acknowledge my co-authors. So we are all lab mates at Columbia University in New York. There's Claudia, Nick, and Caro, who worked on this with me. And so the motivation of this work, and we had a great introduction just before, is that a single LLM can solve many different tasks, and we would like to understand how it does it. So in terms of tasks, we can think of there is like a lot of high-level tasks like coding, translations, text completion. But even more than that, there is like hundreds and thousands of like small tasks that an LLM does. Like some example in the literature of Mechinterp are like greater than task, where we have just a sentence, like the construction lasted from 1615 to 1600 something, and the LLMs understands and implements this task of provided a digit that is greater than 15, because for the meaning of the sentence, we want a digit that is higher than 15. There's other tasks, like similar to like in context learning, that is called induction, where the LLMs learns to repeat a sequence. I don't know if you see my mouse. No, you don't. But yeah, if we have the text like a random pattern, the LLM will learn to like reproduce that pattern. And these two things were like output of ChatGPT. And so how tasks like these are implemented in LLMs, these are like small experiments that people do. And the hypothesis is that LLM implements these tasks in very sparse subnetworks. So we've seen earlier like some layers and hidden units could let the LLM do reverse operation and the antonym operation. And so the idea here is like similar to what scientists have found in the brain, where we have small regions of the brain that are dedicated to specific tasks. And so here in LLMs, they are called circuits. And one question is like, okay, this is a hypothesis that maybe we have circuits in LLM, but we want to know how can we test that our circuits are really real things. So this is for the talk, I'm going to just define these concepts more mathematically. Then I'm going to present some ideal criteria that we would like circuits to adhere to. and then some hypothesis tests to check that if the circuits follow these criteria. So definitions, just as we were saying earlier, the LLMs define a computational graph where the nodes are each like input layer, output layer, and all the intermediary activations, in particular the attention heads. And the edges are like the connections between these layers. And so a specific circuit is a subgraph, and usually a very sparse subgraph in the LLM where we think that this subgraph is responsible for executing a specific task. And so to execute a subgraph, we just take the output of the node in the subgraphs, and we corrupt the other nodes. And so a task, it's a tuple, the way we define it, with a data set of prompts and expected answers, as well as a scoring function that let us know how well we are performing the task. So the example of greater than task is like we have a bunch of examples. So like this time is the war lasted from 1615 to 1600 something. And we would like the logits of any numbers greater than 15 to be higher than the logit of any number smaller than 15. And so we measure performance of the task with this score function. And so criteria, ideal criteria that we would like for circuits, so that these are like 3 criteria we outline in the workshop paper, is that we would like, they're pretty simple criteria, but we would like mechanism preservation. We want the circuits to be as good as the full LLM for the task. We want mechanism localization. So we would like that if we remove the circuits, it should completely eliminate the model ability to perform the task. So like by removing the circuit, I just mean if we instead of we corrupt just the edges of the circuit. And if we do this, we would like the model to output, to fail the task. And an important other fact is like we would like the circuits to be minimal. So we want all edges of a circuit to be important to perform the task. And like if we remove an edge from the circuits, it should hurt the task. And this is important because even though these 2 first criteria seem to make sense, you'll notice that the full LLM satisfy these 2 criteria. Because the full LLM is as good as the full LLM, and removing the full LLM will hurt the task. But another problem is that these criteria can also be exclusive, because imagine you have 2 circuits in your LLM that can perform the same task, and this is a common behavior where we have like backup path in the LLM to solve the same task. So you have 2 circuits called C1 and C2. If you just consider C1, it's not local, because if you remove C1, then C2 can take over. But then if you consider C1 and C2 jointly, they are not minimal, because you could always remove some edges in this thing, and it would still work because you have other edges in the other circuits. And so these are like ideal criteria, but not every LLM can have this criteria satisfied. And so these criteria are like tools for you like to try to see what is the nature of the circuits you find. Another difficulty with regard to these criteria is like how do you quantify them? Because we're saying, oh, we want the circuit to be as good as the full LLM, but how much good is as good? Like they're obviously going to be different in performance, so how much do we quantify that? Same thing with like when do we consider the task to be failed, and how much change is hurting? And so we try to like, in addition to the criteria, we try to like provide some possible way of testing this criteria. And one route we're taking is to use random circuits to establish comparison. So if we want to know how good is like good enough, we draw some random circuits to establish like a Bayes distribution of different scores. And then we compare the score of our target circuits to this Bayes distribution of random circuits. So in terms of like formal hypothesis test, that writes like this, but we just want to basically compare our circuits to a random distribution of circuits. And then we can control this base distribution to modulate the difficulty of the test. So in terms of concrete examples, and simple one here, so here we compare 4 existing circuits from 4 different papers, this induction, this greater than operation I just showed. There is IOI and duck strings, which are 2 other circuits, and we compare how good these circuits are compared to some like random circuits of larger size. And we see, so higher is better. So we see that the size of the base circuits are here on the left, and as we compare to even like much bigger circuits, these circuits are always outperforming even almost full LLMs, just having a small number of edges. So these can serve as a comparison, to compare different circuits. In the same, following this time the minimality criterion, we can compare the edges inside a single circuit. And so we compare removing the edge of a single circuit, we compare this to adding and removing random edges to the circuits. And then what I'm showing here to you is once we do this, we can rank the different edges and how important the edges are in the circuits. And we can try to knock down, here I'm showing when you knock out these edges, and here's the score of the task. We see, so lower is better, and we see that as we knock down some edges, it considerably hurts the performance of the task. And we see that in existing circuits, for some of them, maybe a third of the edges were unnecessary. The circuits were not minimal, and we could just get rid of them. So I have 10 seconds left, and I'm going to jump to conclusion where, in this talk, I just presented 3 ideal criteria so that, to understand properties of circuits, and I presented 2 different tests, one for preservation of circuits and one for minimality. But we have more tests and in our paper for a total of 5 different ones. And if you want to know more about those, you can come to the poster for more details.
Thank you so much for the fantastic talk. If you want to learn more, go check out that poster in the morning session. I'll again say there's a couple of empty seats. If any of the people who are standing could come and take them, that would be great, because we're hitting the capacity of this room, and I want as many people to be able to see these great talks as possible.
Otherwise, move forward, please, because they won't let people in if there's no space there. Just move forward.
Yes. Up next, we have Kiho to talk about geometry of categorical and hierarchical concepts. And if you have a poster that you're going to be presenting in the morning and you haven't put it up yet, feel free to come and stick it up along the side. We've got a bunch of command strips up the front.
Okay, so thank you. Hello, I'm Kiho. Today I'm going to talk about the geometry of categorical and hierarchical concepts in large language models. This is joint work with Yojun, Ibo, and Victor. Understanding how semantic meaning is encoded in the representation spaces of LLMs is a fundamental problem in interpretability. In our paper, we focus on 2 foundational questions in this area. First, how are categorical concepts such as mammal, bird, fish, and reptile represented? Second, how are hierarchical relations between concepts such as the fact that dog is a kind of mammal represented? The challenge here is that a linear direction can only encode a binary concept, so we aim to extend the linear representation hypothesis to more complex concepts and understand their geometric structure. To answer these questions, we focus on the softmax structure in the last transformer layer for next word prediction. The probability distribution over the next words is given by this softmax distribution of the embedding vector lambda x for the input context x, and the unembedding vector gamma y for each token y in the vocabulary. We want to understand the geometry of the embedding and unembedding spaces. we focus on the concepts that affect only the next word. In our previous paper, we showed that the Euclidean inner product does not necessarily encode semantic meaning, since any inner product is compatible with this softmax distribution. This is a problem because each inner product induces a different geometry in the space. Fortunately, we show that there is a particular choice of inner product under which causally separable concepts have orthogonal representations. This allows those concepts to be freely manipulated by adding a direction. In particular, the affine transformation induced by the causal inner product unifies the embedding and unembedding spaces. This is convenient because from now on, we can just look at the unified space where the Euclidean inner product is the causal inner product. So, our high-level strategy is to build up from binary concepts to more complex structures. We begin by defining the concepts. The most general concept is a categorical concept, such as mammal, bird, fish, and reptile. This includes binary concepts as a special case. The binary concepts are partitioned into binary contrast and binary features. First, a binary contrast is a binary variable that contrasts two different attributes. This includes common binary variables, common binary concepts considered in the literature, such as the concept male to female. Next, we define a binary feature as an indicator of whether the next word has a specific attribute. For example, if the feature is bird is true, then the next word will be about a bird. So we will use binary features to build up to binary contrast and categorical concepts. Next, we define the hierarchical structure. We say that Z is subordinate to W if all the values of Z are included in one of the values of W. For example, the binary contrast dog to cat is subordinate to the binary feature for mammal. Also, the binary contrast parrot to eagle is subordinate to the categorical concept with mammal, bird, and fish. Now, we return to the question of how binary concepts are represented. Ideally, if a linear representation exists, then moving the representation in this direction should modify the probability of the target concept in isolation. If adding the direction also modified the off-target concept, then it wouldn't be natural to identify it with the target concept. So here, the off-target concepts are those that can be freely manipulated. That is, those subordinate to or causally separable with the target concept. For example, adding the linear representation for the binary contrast plant to animal should change only that concept without affecting other concepts like mammal to bird or English to French. So, yeah, and formally we can express this under these conditions. Next, we turn to how complex concepts are represented. So, to build up to complex concepts, we need to understand how to compose representations of binary concepts. However, at this stage, the linear representations are just directions without a natural notion of magnitude. So we cannot use vector operation to compose representations. To address this, the next theorem shows how to assign the magnitude to the linear representation. Let me explain the theorem with a specific example. So suppose there exists a linear representation for the binary feature for animal. And we project the unembedding vectors of flower, car, tiger, and dog onto the direction. If the projections are arranged like this, adding this linear representation to the context embedding changes not only the binary feature for animal, but also the logic between flower and call, or between tiger and dog. But we want the subordinate concept to remain unchanged. So therefore, ideally, the projections should be arranged like this. So the tokens relate to animal should share the same projection, and similarly for the other tokens. Then these 2 points determine the magnitude to the linear representation. And now we have a vector representation of the binary feature for the attribute W. With this, the first main result is that if the vector representations exist, semantic hierarchy is encoded as orthogonality. Several types of orthogonality research are shown on the left, and we confirmed these structures in the Gemma 2B model. For example, the right 2D projection plot shows that statement D holds in the Gemma model, as animal minus plant is orthogonal to bird minus mammal. Additionally, we use the full WordNet hierarchy with about 600 features to evaluate the theoretical predictions at scale. The top left heat map is the adjacency matrix of the WordNet hypernym inclusion graph. And these inclusions are clearly visible in the bottom left heat map of the cosine similarity of the vector representation of each feature. However, consistent with statement E, the vectors for child minus parent and parent minus grandparent are orthogonal in the right heat map. So this result is not just a property of the high-dimensional spaces. It truly demonstrates the hierarchical orthogonality. Next, the second main result is that a natural categorical concept where the models can freely manipulate the output values is represented as a simplex with the vector representations as vertices. The right 3D projection plot shows that this statement holds in the Gemma 2B model, as the tetrahedron encodes the categorical concept of mammal, fish, bird, and reptile. We emphasize that these two main results involving differences of representations are only possible because we have vector representations. Mere direction would not suffice. So together, these two main results provides a simple structure like this. So this illustration depicts the overall structure of the hierarchically related concepts. They're represented as the direct sums of simplices. For example, the vector representation for dog can be decomposed into the sum of the vertices in each simplex. In summary, so in the representations of LLMs, categorical concepts are represented as simplices, and hierarchical relations are encoded as orthogonality. If you want more detail, please visit our poster or this archive link. Thank you.
Thanks so much, Kiho, for a fantastic talk. I love the attention to figures. Next up, we have Shinting talking about inversion view, which I think was one of the most creative papers I think I saw submitted to this workshop. So I am very excited for the talk. A game for anyone who wants to play along at home is we're going to be announcing the top 3 top paper prizes at the end of all the orals. And if you want to play along at home, you can try to predict which ones should get the best prizes.
Oh, shit.
Yeah, take it away.
Yeah, I'm trying to make sure you can see my cursor, but it seems it doesn't work.
Oh no, I'm so sorry. Technical issues?
Like this thing.
No, I think, oh sorry. Yeah, sorry, it's not working.
Is that this can work?
In the meantime, there's still some seats. You can take them. There's free real estate.
So that's. Oh yeah.
You don't
Okay.
have to stand and increase fire hazards. It's fine.
As in, like, please try to take a seat if possible.
Okay, so
Literally at capacity of this room.
Can I start? Yep. Hello everyone, I'm Xinting. Today I'm very happy to be here and present our work in version view, a general purpose method for reading information from neural activations. So in this paper, we want to answer this question, what information is encoded in neural activations? Can I have that? Yeah, so here we show an activation taken from an arbitrary place in the neural network, and when processing the input, we want to figure out what information it contains. So we answer this in terms of pre-image, which is that is the subset of inputs that give rise to the same or similar activation. And we say that the commonality in the pre-image is the encoded information. And we refer the activation and its corresponding input we're studying as the query activation and query input. So why does this idea make sense? Imagine that if the activation contains only the information that John is the subject, then given an input, John is on leave today, and its corresponding activation in the vector space. If we change other parts of the input, for example, we change it to John has a cute dog, then its corresponding activation should not change. Otherwise, it encodes information about other parts of the input. So we will see inputs where the John is the subject are represented as roughly the same activation. So from another perspective, we say that the activation represents the whole pre-image. When it's observed by the downstream model components, the commonality is the encoded information. So this raises a new question: how do we find the pre-image efficiently? This is hard because the input space is quite large. So we train a decoder conditioned on the activation. So it takes the activation and generates the input. And we then feed back to this input. We sample this input and then feed back to the original model to compute the distance. So we know we can filter out those inputs outside of the pre-image. So this is basically our methodology. So let's look at the first case study where we apply inversion view to a small transformer trained on a synthetic task, character counting. So the inputs are like, where's my cursor? So the inputs are like this. The task is to count how many times the target character occurs before the pipe sign, which is a separator token. And the model needs to predict the last token, which is the count after the column token. So we first noticed that in attention layer 0, the target character attends to the same character in the previous context. And so we think the counting might happen there. So we look at the residual stream after the attention layer 0 at the position of the target character, and we see, and we show the generated samples on the right. In the first column, you see the numbers. The numbers show the distance between the activation resulting from this input and the query activation. And the distance is a normalized version of Euclidean distance. And we set the threshold to be 0.1, so that these inputs with distance smaller than 0.1 would be inside the pre-image. And we also show the true count in the second column. The true count is the count of the target character because the decoder sometimes generates run count. And the B and E are the beginning and end of sentence token. So in the pre-image, we see that the common thing is that the G is always the target character. And also the count is either 3 or 4, so it's approximately encoded. So we can see that the counting really happens in attention layer 0. And if we move to another place, we see that key difference is that the count information is reinforced by the MLP layer. Because now we see in the pre-image, there's only count 3, and count 4 and 2 becomes much more distant than before. So we want to emphasize that due to space limit, we only show around 10 examples here, but in practice, we usually rapidly inspect much more examples. And we found that the same pattern holds in general. Let's move to the second layer, like in layer 1, we see the token character, like the column token attends to the target character exclusively. And so an inversion view tells us the information moved by the attention head to the residual stream of the column token is only the count. And the target, because we see and the identity of the target character is forgotten, because we see in the pre-image now they become interchangeable. So far we have inferred a simple algorithm implemented by the model. It first counts in layer 0, and then this count information is amplified. Then only the count information is moved to the column token. And we also verify this causally and quantitatively. And the second case study is about indirect object identification, or IOI circuit, in GPT-2 small, previously found by Wang and others. And the inputs are like this. The model needs to predict the last token, Mary, which is the object of the main clause, and this name already appears in the previous initial subclass. So we apply inversion view to the outputs of the heads in IOI circuit and check if the information read out by inversion view is the same as those from Wang and others. For example, here we show the case of head 9.9, which Wang and others identified as a Nambuva head. On the top, we show the attention score, attention weights. The color indicates how much the token 2 attends to other tokens. And so in the pre-image, we see that the object name Justin is always there and is always the object. So here we observe the same information as Wang and others. And likewise, applying inversion view to other outputs of the heads in IOI circuit, we found that we obtain information highly agreeing with Wang and others. So, as the third case study, in the third case study, we interpret a 2-layer transformer trained on the 3-digit addition task. And the inputs are like this. And the model is trained on next token prediction. So here we show an example of the pre-image of output of a head in layer 1. In this head, the token 1 attends to the equal sign. And we see that the encoded information is the 2 digits in the hundreds place, because in the pre-image, they are 9 and 8 or 8 and 9. And more importantly, the sum of the tens place digits is also encoded, because we see it's 2 plus 7, 6 plus 3, 1 plus 8. And the color on each generated token indicates its relevance to the query activation. And likewise, applying inversion view, we reverse engineer the algorithm implemented by the model and verify it causally and quantitatively. So to test the applicability of the inversion view on larger models, we also apply it to GPT-2 XL. Here we studied the task of factual recall. And the inputs are like this. The model needs to predict the attribute given a prompt containing the subject and the relation. So, So since we are in Austria, let's look at an example of an Austrian economist. Here we show the pre-image of a certain attention head output in upper layers, and we see that the encoded information is about economists, because in the pre-image we see the names of economists: Adam Smith, Mises, Milton Friedman. So, and on the other hand, if we look at another head on the if we look at another head on the same example, we see a different information. This time the information is about nationality. We see names of people who are from Austria or countries around Austria. For example, von Neumann, Freud, Wittgenstein, and Kafka. So we apply inversion view and we show that inversion view also produces interpretable result on larger models. So, in conclusion, we present inversion view, an effective method for decoding information from neural activations. We apply in 4 case studies and show that it can reveal various types of information. And more importantly, there is a lot of potential left to explore in the future work. Thank you.
Awesome. Thanks so much for the fantastic talk. I am super excited to see people apply inversion view. Up next, we have Aaron talking about missed causes and problems of counterfactual effects, notable for being our one single author oral. So yeah, hope you can all join me in welcoming Aaron to the stage.
All right, hi everyone. I'm Aaron Mueller, a postdoc at Northeastern in the Technion. And today I'll be talking about sort of a more theory-driven set of ideas on the nature of cause and effect and how counterfactual theories might cause us to bias our results in Mech-Interp. So what does it actually mean to say that something causes something else? This is sort of a question that philosophers are still arguing largely about. But one sort of predominant theory over the last few decades has been the counterfactual theory. This idea was first proposed in the 18th century by David Hume, but really it was formalized by David Lewis in the 1970s into what we now recognize as the counterfactual theory. And the idea is essentially that you can only say a cause truly causes an effect if when the cause happens, the effect also happens, and when the cause does not happen, holding all else constant, the effect would not have happened. So in other words, you need access to a scenario that didn't actually occur, or a counterfactual, in order to be able to make arguments about what actually caused something else. So in Mech-Interp, counterfactuals are pretty ubiquitous. If we think about one of the most common techniques in Mech-Interp, activation patching, this is essentially just a counterfactual intervention to a language model's neurons or attention heads. So for example, given a task like subject-verb agreement, what we can do to quantify the importance of every node in the model is to replace the activation of a given component with what it would have been given some alternate input that flips the answer. And then, after doing this intervention, we can measure the causal impact of this by measuring how much the probability of some output term changes, or measuring other such changes in model behaviors. So if we apply this to every single component in the model, we could end up with this causal graph that represents the task-specific circuit for a given task. And this is just one example. There are many other techniques like alignment search or Rome, which also rely on counterfactual interventions. So it seems like Mech-Interp in general is taking the counterfactual theory for granted, since it is such an easily applicable idea. But in this talk, I'm going to argue that counterfactuals have a couple key issues that might bias our results if we don't explicitly handle them. And these are overdetermination and non-transitivity. So the first one, overdetermination, is essentially about redundant causes. So imagine a causal graph that looks like this, where 2 people throw rocks at a glass bottle at the exact same time. If we ablate one of these causes, then C will still end up happening, and therefore C is not counterfactually dependent on just one of these causes alone. And the same thing would happen if we only ablated B but not A. So does this therefore mean that A or B did not cause C? This is kind of an uncomfortable conclusion that I think reflects a difference between the counterfactual theory's predictions and actual causality. So thinking more about neural networks, if we have a situation where 2 causes are both necessary for a given effect to occur, then ablating only one of them will allow us to discover the cause. But if we have a case where 2 causes are independently sufficient to cause something to happen, then ablating only one of them will result in no measurable change to the outputs. And therefore, we would falsely conclude that neither of these components has any impact. A more pernicious form of overdetermination is preemption, where one cause, when it is active, suppresses the causal impact of something else. So we know that redundancy is very common in neural networks from past work. So the question that then arises is how many causes have we been missing this whole time? Furthermore, we've already actually seen plenty of examples of preemption in past work. Think about things like Hydra effects or backup heads. This required us to ablate one upstream cause before we were able to quantify the causal impact of some other cause later on. So this reveals that intervening only on single components at a time is going to be problematic and not lead to very robust results. In order to actually robustly recover the mechanisms underlying some behavior, we're going to need multi-component interventions. Furthermore, we could also use a mixture of intervention types as advocated by certain people who I think are here right now. And where you could also use multiple interventions to test both necessariness and sufficiency at the same time. So the next big issue with counterfactuals is non-transitivity. So it's pretty natural to assume that if A causes B and B causes C, therefore A must cause C. But this is actually a fallacy. So if we consider this example from Ned Hall, where a hiker is walking up a mountain and a boulder starts rolling towards them, the hiker could then move out of the way or duck out of the way and then end up surviving. But in this case, while each of these local dependencies holds, does it really make sense to say that the boulder rolling toward the hiker caused them to live? This is a case where non-transitivity would hold, but there are plenty of cases where causality is transitive. So what then is the fundamental difference between cases where causality is or is not transitive? So there are two sets of conditions that will guarantee the transitivity of counterfactual dependence. One of these being that you can have multiple causes, which together result in distinct effects deterministically. So the reason that the hiker example violates this is because whether or not A happens, the final result of the hiker living is the same. So this example violates this set of conditions. There's also a sufficient but not necessary set of conditions, which essentially relies on the intuition of causal bottlenecks. So this is the idea that if A must pass through B on every causal path that it has to C, and A also determines all the values of B, then we can conclude that A directly causes C. But in this case, this isn't really true, because the hiker has many ways they could possibly avoid this boulder rolling towards them. So thinking about neural networks, I would argue that both of these sets of conditions are very unlikely to hold in most practical cases. The first set's unlikely because I think it's rare that a small set of interpretable nodes at the neuron or attention head level will be strong enough to sufficiently determine the value of downstream components or the outputs directly. Rather, all the components required to determine some outcome tend to be non-interpretable, like full layers or other such bottlenecks. Furthermore, the second set of conditions is unlikely because if we think about the level of neurons and how many neurons there are in a given model in a layer, it seems pretty unlikely that we'll have any bottlenecks at the neuron level. Now, these are guaranteed to occur at the layer level, but layers, unfortunately, are not interpretable. So this presents a challenge and a trade-off between being able to interpret these edges deterministically and transitively versus being able to interpret the nodes that compose these causal graphs. So I don't have time to go through the set of results that I'm about to present, unfortunately, but I encourage you to check out the poster if you're interested in this next set of experiments. So we've seen so far that there's actually a distinction between local dependencies that affect other important components in the model and global dependencies which directly impact the output. So should we actually include any of these local dependencies then? I think it'd be really tempting to just throw those away since they don't impact the output directly. But I would argue against this as a general recommendation because these could help us understand how the intermediate abstractions are composed by the model. So Samuel Marks et al. Found this interesting behavior where language models are able to predict the upcoming number in a list of numbers given the prior sequence of numbers. They found that this was the intersection of two distinct mechanisms, a general succession mechanism that predicts the next item in lists, and a narrow induction mechanism that only predicts copies of previous terms on specific kinds of inputs. So in the sparse feature circuit that they've discovered for this behavior, they found that the succession feature arose spontaneously at layer 3 with no in edges to it anywhere. So this is kind of confusing because obviously this must have been composed from some aspect of the input behaviors. It's just that none of these dependencies actually affected the outputs directly. So where did this actually come from? The short answer is basically that most of these features that compose the succession feature are from numeric inputs. All the features in this circuit activate on things like 1, 2, or 3, or lists of numbers. So this tells us that this is actually a numeric succession behavior. So the fact that we know that this is numeric succession helps us understand the mechanism better and predict whether it will be active on future inputs. So while these local dependencies didn't directly affect the output, they were still helpful in our understanding of how the model was composing this abstraction from its inputs. So these two issues present a few key challenges for future work in mechanistic interpretability. The first of which being, what should we do with these nodes that are locally important but have little effect on the output? Well, as I've argued, I think if the goal is to understand and predict model generalization, I think we need to be including at least some of these local dependencies to better understand these behaviors. But if your goal is instead to simply find the components that contribute to high performance, maybe for model editing purposes, global dependencies might be sufficient. Although I think that global dependencies might be able to partially explain why things like causal localizations don't reflect the best locations for model editing. So this actually needs some empirical validation. Now, including local dependencies will cause the size of our circuits to explode pretty quickly. So to overcome this, I also advocate for using more diverse data sets so that we can exclude more spurious or specific mechanisms from our graphs. Second, how can we increase our recall of these overdetermined causes while not significantly harming the precision of our methods? Currently, greedy search methods are kind of the state of the art for looking over sets of components. But I think ultimately we're going to be required to do interventions to multiple components simultaneously to get robust results. Furthermore, I think we need to quantify how commonly these issues actually occur in typical neural networks, because it's currently not clear how common overdetermination really is. And finally, are counterfactual theories of causality sufficient for our purposes? I would argue yes, but I think we need to handle these issues a bit more carefully. Now, there are alternate theories of causality out there. One really interesting and applicable one would be causality as description length reduction, where the inclusion of a cause reduces the number of bits you need to explain some downstream effect. But that said, I think for now, counterfactual theories are still the most actionable for analyzing neural networks. We have the complete causal graphs and all the tools we need to intervene on them, but I think what we need more of is simply searches for better kinds of causal units of analysis, as well as better ways of scalably searching over all of these issues. So the issue isn't that the counterfactual theory has problems, but rather that we just haven't sufficiently handled them quite yet. Thank you.
Amazing. Thank you so much to Aaron for an incredibly thought-provoking talk. Or at least, I'm having thoughts and the talk happened, but who knows if there was a causal link. All right, now we have Rico for our final oral on measuring progress in dictionary learning with board game models. Sadly, the lead author, Adam Carbonen, wasn't able to make it at the last minute due to stupid passport issues, but I'm very glad we have another author, Rico, here in his place. Some logistical notes. There's a bunch of people outside who want to get in, but aren't allowed in. The fewer people there are near the doors, the more we can have inside.
We don't have a mic.
Sorry?
You don't have a mic.
Oh, good point. All right. The more people we have away from the doors, the more people can get in. So if people, I don't know, want to come sit at the front or sit in the middle or just like be stacked more than one level deep along the sides, that would be fantastic.
Or you might hate other people, in which case stand by the doors and block them in.
I mean, reasonable. I mean, you know, you are kind of reaping the rewards of being more dedicated and getting here earlier. But yeah, and I'll hand over to Rico. Oh, yes. We're going to be transitioning to spotlights pretty rapidly after orals. So if the 10 to 15 people doing morning spotlights could make sure they're lined up along the wall in the order reflected on the website, that would be fantastic. Ask Atticus if you don't know where you should be standing. And if you aren't queuing up, I don't know, we might just skip your slot, who knows. All right. I will hand over to Rico.
All right.
Thanks a lot.
Thanks, Neil. Yeah, I'm Rico Angel, and I'm here presenting our paper, Measuring Progress in Dictionary Learning for Language Model Interpretability with Board Game Models. And I'm presenting on behalf of the first author, Adam, who couldn't be here, unfortunately. So in this paper, we use language models trained on board game transcripts as a testbed for benchmarking sparse dictionary learning techniques. And we also introduce a new sparse dictionary learning technique as a secondary contribution. So one of the central questions of mechanistic interpretability at the moment is, what are the fundamental units of representation? And the superposition hypothesis is the prevailing theory for how neural networks represent these fundamental units. And superposition hypothesizes that model activations are composed of a linear combination of a relatively small number of latent feature directions. And there are more possible feature directions than dimensions in the vector space. And the goal is to automatically decompose these internal network activations into these latent feature directions. So the common approach for decomposing these internal activations into feature representations is to train a sparse autoencoder to reconstruct the internal activations using as few hidden units as possible in the autoencoder. This method is simple and efficient, and it's entirely unsupervised. So using SAEs, we can begin to break down the model's computation into understandable components. As a result, there have been a flurry of new SAE architectures and loss functions, including gated SAEs, top K, jump ReLU, and the list goes on. But how do we determine which of these models is best? So there's a bunch of different current evaluation strategies. For example, unsupervised proxy metrics such as loss recovered and L0 have been used to quantitatively compare SAEs. Loss recovered is a measure of the fidelity of the SAE's reconstruction of the model activations, and L0 is a measure of the sparsity of the SAE activations. These are entirely unsupervised, but they also don't necessarily correlate with interpretability. So another commonly used evaluation strategy is subjective interpretability or manual inspection. So in this case, we take the maximum activating inputs for a feature in the SAE, and we try to sift through those examples and identify some kind of pattern and try to interpret them. This is nice, but it's not really scalable. It doesn't work for all SAE features, and it's subjective. There have also been some. Did it just die? Yeah. I can use this one.
Is this working?
So there have also been. Is this working? Oh, okay. There have been some recent other examples of different automated natural language evaluations.
So well right now.
So in this example on the bottom right here, we show an example from Anthropic where they tried to identify whether or not there are SAE features for particular periodic like chemical elements. And the way they do this is that they perform a string match on the input and say, oh, is this particular element present in the input? And then they try to see if there exists an SAE feature that activates, it correlates with this word being present in the input. So while this is interesting, there are obvious limitations to these strategies, and these evaluation strategies are used because there's no underlying measurable ground truth in natural language. So in natural language, the reason that these evaluation strategies aren't the best is because we really don't know what the feature space should look like. Natural language is highly unstructured, and we don't really know what the features should be or what concepts should be represented in the model. So in contrast, board games, there is exact deterministic ground truth, and there is which cannot be obtained from like a syntactic level of pattern matching like the chemical element example. So in this work, we consider board game language models. So the one we consider both chess and Othello, but we're going to focus on chess because it's a little more interesting for the sake of this talk. So on the left here, we see what's called a PGN string. It's a transcript of a chess game. And this ChessGPT is trained to predict the next character in transcripts of real games. And what's really great about this is that there's a deterministic function that determines the state of the chessboard on the right from the PGN string on the left. And in this model, we can extract explicit and deterministic state from the internals of the model. So, and we also consider a similar model trained on Othello GPT. So in order to start evaluating these language models, these board game language models, we define several board state properties. So these board state properties are binary functions on the state of the chessboard or the Othello board, and they are, properties like, is there a knight on f3? Simple piece on square properties, and then all the way up to like high-level chess strategy properties. So for example, on the right, there is this, is there a pin present a board state property? And so we manually write down, functions to evaluate over 1,000 of these BSPs, and then we can use this to automatically find features in the SAE connected to these board state properties. So as an example of how complex this can get, we actually find a SAE feature representing en passant. So en passant's a kind of a corner case rule in chess, and it's important to note that even though I'm showing an example here, this is not streetlight interpretability. This is a feature that activates with over 90% accuracy when en passant is available in the board state. And as you can see on the bottom here, we show these like blue highlighting here is, and that's the only place that the feature is active, right after en passant is available. And there's many more examples like this for this particular SAE feature. So our first contribution is using our BSPs, we construct two supervised SAE metrics. First is coverage, and this tries to answer the question of how well do the features align with the individual BSPs, similar to monosemanticity. And then the second metric is board reconstruction, which is how well can we reconstruct the board given the SAE features. Now, this is more of like how well does the SAE model the internals of the language model's world model. So in the sake of coverage, we basically write down every BSP and we check every SAE feature and we try to find the SAE feature that has the max F1 score in classifying the BSP as ground truth. And we do this for all the BSPs and we average them, and that's our coverage metric. So then our second metric is board reconstruction. So how well can we reconstruct the board given SAE features? So the first step in computing this metric is we identify high precision SAE features, basically meaning when the feature is active, the BSP is present. And we do this for every feature. And then we reconstruct a partial board state based on these feature activations, and then compute the F1 score between the predicted reconstructed board state and the actual board state. So our second contribution is a different SAE training technique, which we call p-annealing, and all we do in this instance is replace the L1 norm minimization with an LP P normalization, and we anneal P during training from 1 down to 0.2 in this case over the training process. So how well do these metrics work? So in this plot, we have trained 4 different types of SAEs, and we plot on the x-axis the L0 and the y-axis the loss recovered, which is are these unsupervised proxy metrics, and then the color of each point corresponds to the board state property metric called the coverage metric. And in this case, a lighter color corresponds to a higher coverage of the board state. And what we see is that we have the standard SAEs on the lower line, and then we see a Pareto improvement for all of the new types of SAEs we see. But it isn't quite clear which of these SAEs is better. But if we instead plot the coverage board state of the chessboard state metric on the y-axis and the L0 on the x-axis, we actually see that our coverage metric can differentiate the SAEs at that elbow of the Pareto curve. So I'm a little over time. Come see our poster. We're at the second session. Thank you.
Awesome. Thanks so much, Rico, and to all of our other great oral speakers. All right, I'm going to briefly announce the papers that have won prizes in reverse order for maximum suspense, and then we're going to move on to our hyperspeedy spotlights. All right, so first, we have an honorable mention for top paper to measuring progress in dictionary learning for language model interpretability with board game models. Can everyone who was an author on that paper stand up? All right, we have 2 authors in the house. And is David an author? Yes. Beautiful. All right, we have 3 authors in the house. Great work, all. If you didn't think David was cool already, you'd better think he's cool now. All right. Second honorable mention goes to missed causes and ambiguous effects, where we have all of the authors in the house, I think. Right there. Woo! Yep, I think it's really great to just bring more rigor to a lot of the implicit assumptions we make with the techniques in this field, so fabulous work. All right, now for our first actual prize. The third place with a $250 cash award goes to hypothesis testing the circuit hypothesis. Can all the authors stand up? Woo! Great work, all. Second prize for $500 goes to Inversion View. Can people stand up? Woo! At the back. And by process of elimination, our $1,000 first prize goes to the geometry of categorical and hierarchical features. Can I get a round of applause? Woo! And yeah, can everyone join me in a final round of applause for just all of our oral authors for their fantastic work? Great. Also, okay, people along the sides, please raise your hand if you're about to give a spotlight talk. Great. Can everyone who didn't raise their hand please move into the middle or sit down at the front or something? Because there is a line of people outside who would like to be in this workshop. No, move forwards. This is an instruction. All right. So we are now going to start doing spotlights. In the interest of time, these are strictly enforced 2-minute lightning talks. I will just start clapping softly and then increasingly loudly as we get to 2 minutes, and just advance, ominously towards the stage. And yeah, I will hand over to Florian to talk about Comgrow. Yep, take it away.
Hi everyone. So I'm sure I'm not the only one here who is frustrated by how difficult it is to debug and analyze and inspect neural networks. And to fix this problem, I've created a tool called Comgrow, which stands for Computation Graph Analysis. You can use this to record and then in a GUI traverse your computation graph and inspect all the statistics on basically anything that happens in your network at any time during training. But you can't even just look at statistics, you can even drill down and look at, for example, give me all the pictures of cats that were wrongly classified and let me inspect individual neurons for those. And then you can even go and say, well, let's traverse our computation graph, check for gradients, check for weird outliers, check for statistics, and see if we can find the source of the bug. And if we have found the solution, we can even compare our interventions to the original, and with just a few mouse clicks, get comparisons between all of the different things we tried and their effects on different parts of the computation graph in very little time. So the main benefit here is, you record this once, extract all the data once, and then later on, no matter what your research question ends up being, it will probably take you only a couple of mouse clicks to find a comparison for exactly the thing you want to test. And in this way, you save yourself an enormous amount of time because you no longer have to rerun your code every night. You just run it once, and whenever you have an idea, it just takes a couple of seconds to test and verify a hypothesis of yours. And if you're interested in this, I'd be happy to explain this and a whole bunch of additional use cases at the poster.
Hello. Hi, my name's Dan. Our work is on improving sparse dictionary learning, and this was a collaboration between Apollo Research and Jordan Taylor of MATS. So one problem with SAEs is that they're not incentivized to learn the features that maximally explain the network performance. And this manifests in learning less important or completely irrelevant features. To address this, we introduced a new type of SAE called end-to-end SAE. And this has an extra term which measures the KL divergence between the network with the SAE in it and the original network. We also introduce end-to-end downstream, which the idea here is to prevent the network with the SAE taking different pathways through different computational pathways through the network. And so how do these work? Very well. End-to-end SAEs require fewer than half the active features per data point, this is the L0 metric, to explain the same amount of performance. And we also find that we need fewer features in total over the whole data set. We show some other results in the paper, such as end-to-end SAEs being more just as interpretable as local SAEs. And we do some geometric analyses of all of these SAEs. One downside is that we find that end-to-end SAEs are about 2.5 times slower to train, on GPT-2 at least. But we think we can improve this by, for example, initializing with local SAEs and then fine-tuning with end-to-end SAEs, or doing something similar to that. Yeah, thanks for listening. You can scan this for our paper and come see our poster. Cheers.
When did you put them in?
I think yesterday.
I didn't see them when I was copying them this morning.
Okay, so can I use?
Yeah. Okay. Technical issues. This will be moved to the end of this bullet here. We'll get you later. And the next speaker, please come on.
Oh, all right, go ahead.
And is this an old version of it? Okay.
Well, people evade on deadline in the slides.
Okay. We did a really cool project on proofs and Mechanistic, and I'd love to talk about it at the poster. Here I'm just going to give you the takeaways for non-proofy Mechanistic projects. You can think of Mechanistic as taking large models and compressing explanations about them. And we want to know how much compression do we get. We want a quantitative metric on compression, and we use proof length as that metric. And this is an old version, so skipping that slide. The baseline approach is to just run inference on your model. You can run anywhere between 0% of the data points and 100% of the data points. With 0% of the data points, you get the trivial proof that the accuracy is greater than or equal to 0%. And with 100% of the data points, you get whatever the actual accuracy of the model is. And the obvious hypothesis from Mechanistic is that understanding of structure can improve on this baseline. We tested this empirically on a toy model, and by formalizing proofs with varying degrees of mechanistic understanding, and found indeed that we can improve on the linear baseline. As you go from left to right, as you go from right to left here, you'll see that we add mechanistic understanding, and we can get better bounds than the linear baseline. But the puzzle here is that even with more mechanistic understanding, we can't fully recover we can't fully recover the true accuracy of the model. And the reason for this is that even after you account for all the structure in the model, there's still structureless noise. There's still compounding errors that we can't cheaply bound because we lack understanding. Thank you.
Hi, everyone. I'm Aaron Phillip. I'm a co-author on this paper focused on interpreting attention layers and vision transformers. So past studies of semanticity and transformers have mostly focused on the MLP blocks and on finding individual feature directions, whereas here we focus on pairs of feature directions in attention blocks. In the blue box, I'm showing the typical definition of attention. We propose that decomposing the query key matrix product via the singular value decomposition provides pairs of natural feature directions in which to study tokens. Why? Because if a query token is aligned with a left singular vector, it's only going to attend to key tokens aligned with the corresponding right singular vector. From now on, I'm going to call each pair of left-right vectors a singular mode. Yeah, sure. Okay, down here, I've shown a key result from our paper in which we found we could associate specific singular modes in the model with semantically meaningful groups of images. So each row shows the images that maximally activate a specific mode in the model. The first two rows are from early modes in the Dino model, the latter two from later layers. And the heat maps next to each picture show which tokens a left and right singular vector are highlighting in specific. So cyan indicates a left, which corresponds to a query. Red indicates a right, corresponding to a key. One of our general observations was that right and left vectors both highlight similar areas in the early layers. So for example, you can see the leopard or the zebra and the accordion stripe texture are both being highlighted by left and rights. Whereas in later layers, they start to focus on different things. So for example, you see the mug and the teapot being highlighted and contrasted with the background. Or down here at the bottom, the person's being highlighted by one, the thing they're holding is highlighted by another. So information's kind of flowing between two objects in the picture. So although this is a single example, we analyzed modes across a bunch of different vision transformers. And we have many more supporting examples in our paper. We also found, on average, left and right singular value pairs, singular vector pairs are more aligned in early layers compared to later ones, as shown by that grayscale plot in the upper left. That's a lot that I just threw at you. Come see my poster, it's on the left, slightly crooked. And yeah, thank you.
Hi, I'm Daniel, and I'm here to talk about Penzai and TreeScope, which is a toolkit for interpreting, visualizing, and editing models, and in general, just sort of doing weird things with models interactively by treating them as data. Well, they're in the wrong order, but that's fine. Yeah, so Penzai is the first library. This is a JAX library for manipulating models by representing them as data structures. And it focuses on making it easy to do stuff with models after they've been trained. So it features a combinator-based design that tries to simplify the forward pass and lets you sort of pull out pieces of it. It includes a selector system that lets you modify pieces. It uses named axes and supports visualization as sort of a first-class part of the tool. And then there's also TreeScope, which is the companion pretty printer, an interactive visualizer that integrates with IPython and Colab notebooks that lets you sort of interactively poke at the insides of models, visualize arrays with arbitrary dimensions. Originally, this was designed for Penzai, but now it also does support PyTorch models as well. There's the QR code. Yes, so if you can find the documentation here. You can also come to the poster.
The theme might be. Okay, well. Yeah, we'll just go for it. Hey, I'm Jacob. This is Phil. Neil is Neil, and all right. And yeah, let's get into this. Wait, this is out of order. Wait, all of our slides are gone. We'll do this at the end.
Okay, well, we do have one slide, right?
Let's just.
Okay. Feature interest.
Hello, everyone. Today I'm going to talk about a toy setting we are building, trying to understand the skill composition and how language models learn complex skills via combining simple skills. So here the intuition was like those models usually learn some simple skills and compose them via in-context learning to perform complex tasks. Here our toy setting is like we want the model to learn a collection of modular linear functions where those task vectors A, B are hidden, and we give X, Y, and Z the answer prediction, let the model learn in context and predict the answer. And with this setting, when we give, it turns out we need enough number of task vectors to force the model to learn the composition skills. Otherwise, we will just memorize the thing and do each task individually. And interestingly, we identify the algorithm that the model implements. So there's an algorithm that it first do rescale of the in-context examples. So whenever you give a new question, it will rescale the existing examples and try to match the prediction by just rescale for several contexts. And then the model learns to combine things, which is better than just the rescale of those existing examples. And we also identified the simple skills that need to implement that algorithm. And through some embeddings, it implements some circle-like pattern in embedding layers, and we find highly structured structures like in attention features. And on top of that, we find very specialized neurons in MLP layers, which combine all those skills, like it makes a prediction. And for the details, please come to our poster there. Thank you.
Hi everyone, my name is Clément, and I present to you our work on how do llamas process multilingual text. And so basically the mesmerizing research question we tried to answer was like, do LLMs share concept representation across languages? We draw two hypotheses. The first one would be like concept and language are like represented independently, and so like a book, no matter the language it's written of, will be represented in the same way in the residual stream. And the other hypothesis would be that the model represents like concept depending on the language. So the book in English would be one direction, the book in German would be another one. And so to choose between which of those two hypotheses is a true one, we argue that if you take the mean in the first case, so the mean of the book across different languages, you will get like still a good representation of what is a book. While in the other case, it's not clear what the mean vector would represent. And so how do we test that? Easy, we ask the model to translate the mean representation. And so are they able to do that? Kind of, yeah. So if you ask the model to translate the mean representation, it actually improves performance. And so that's like our main result. And so this means like we are probably in H1. And so if you want to know more and see like cool diagrams, and like good explanation, come to our poster, which is like at the back on the left. Thank you.
We're just going to take a 1 minute technical break to switch presentations.
By switch, I mean open.
Yes.
Sorry, guys.
Remove slides that hopefully have Q&As.
Yes.
No, no promises.
Oh boy, that disappeared. Wait, what happened to the...
While we wait, can everyone join me in a round of applause for our great spotlight so far?
What happened to the thing?
Gaze at the posters and try to figure out which one we're most excited to go to. We might even have slides up there sometime. Who knows?
Yeah. That's not it. No. Can you just... Hey, sorry, I can't see the... I only see this. You want this presentation? No, I want the other one down so I can use it again. Because I need to press present right now. Yeah, like I want the other one the current one that's on your screen.
Ola's a little lesson about having earlier and clearer slides. So apologies for all the issues.
Can you just... Yeah, that's what I'm doing right now.
But with all the suspense built, I'm sure the remaining half of the spotlights will be even more glorious. Especially our first spotlight after the break. I expect great for
this one. Yeah. No, that didn't work. Great. All right, fingers crossed that worked.
All right, thank you. So there's been a lot of excitement around this idea of the linear representation hypothesis, that a vector that represents the state of a neural network can be decomposed into feature vectors. So if you're talking about a scene with a duck and a capybara, you have a vector that's the state that is the sum of a duck vector and a capybara vector. And it's a beautiful first step, but it's also clearly only a first step. Because if you think about anything complex, you realize actually it's more than knowing just the concepts that are involved, but you have to know the relations between them. So you need some kind of way of composing features that goes beyond just vector addition, something hopefully non-commutative. Okay, so how could that possibly work? So the interesting thing is this is a question, it dates back a long time. You know, Frank Rosenblatt, the inventor of perceptrons, was writing about this in 1961. And I think as we think about it, it's worth knowing about all the ideas that were proposed over the past decades. Many of them, I think, have gotten a little bit dusty and have not been explored in the context of modern neural networks, which is an interesting opportunity. So I won't recapitulate a whole survey here, but a big part of the paper is about exactly this, surveying what has been done and some previous interesting ideas, both modern and dusty. But another part of the paper is explaining why this is so important. So there's obviously a basic science aspect to this, but much more than that, even if all you were interested in was individual features, I claim that understanding the relational composition is going to be really important to using them. And there's a lot of reasons to kind of speculate that, you know, if you don't take into account relational composition, whatever it is, you'll get a lot of spurious features. You'll see features that are not good for controlling, even though they're good for reading, and so forth. To find out more, come to my poster in the back.
Hi, everyone. My name is Ilan, and I'm presenting our work, Lost in the Crowd. The lead author, Sarah, unfortunately couldn't be here. And also, I have to run right after this, so if you have any questions, find Naomi. She'll be on the panel later. So let's imagine that we train a small transformer to add 2 3-digit numbers, a very simple task, and we look at the aggregate loss, and there's some regions where it goes down and some regions where it's kind of like seems to go down less, but there's a lot of like hidden information in this trajectory that might not be immediately obvious. And in fact, if we decompose this loss by which the target like place is, you know, if you're predicting the 1000th place or the 100th place, we can see that there's very distinct and different behavior across these different tasks. And so we argue that these transitions sort of represent different capabilities of the model. For example, this blue line means that the first thing the model is doing is learning whether the 1000th place is a 1 or a 0. And so there's a lot of information to be gained here about what the model is learning over time by decomposing according to these different tasks. So some recent work identifies particular instabilities or inflections in training, and each training point's loss conveys meaningful information. And so by clustering using this information, we can, in an unsupervised fashion, identify meaningful subsets of the training data that represent the model's ability to solve certain tasks. And so we explore an improved approach to doing this, not just looking at the loss, but we extend loss change allocation by decomposing according to the individual training points, using a second order term to better approximate this decomposition. And instead of decomposing along individual parameters, which is like axis aligned, we do it along arbitrary bases, which we uncover via looking at the loss curvature during training, which provides a more meaningful clustering. So come check out our poster and go ask Naomi if you have any questions.
Hello, everyone. I'm Kurt, and I will be talking about our paper about representations of sentiment. So our research question was how language models internally represent sentiment, both positive and negative, and how this is used in subsequent predictions. So we took a fairly simple data set of positive and negatively valenced words, and we used a variety of methods to try to find directions. So these are the methods we used, and they all found pretty tightly correlated positive and negative directions along a single axis. So to evaluate the correlational characteristics of this, we looked at how it activates on text. As you might expect, it generally activates on a variety of contexts in positive and negative situations. It also correlates highly with labels to positive and negative text done by GPT-4. We also performed causal evaluation, patching the direction specifically and seeing what its effect was on a task where the model was supposed to predict a positive or negative sentiment. ending and found that this was highly causal and was able to flip the logits in most cases. Another thing we found was a summarization motif, which is a mechanism by which models tend to take positive or negative sentiment and put this in punctuation points or keywords. In this case, it's the token movie in GPT-2. And then later use that in downstream predictions. And this is causal as well, to the extent that sometimes if you ablate the sentiment among the preceding phrase and versus doing that to the punctuation that follows it, the effect is equivalent. And then we validated this on real-world data sets as well. And that's our core results. So that's it. Thank you.
Okay. Hi, everyone. I'm Michael, and I'm going to tell you all how to go beyond circuit overlap when finding model mechanisms. So my poster is about circuits. You guys have seen a lot of them, these collections of nodes and edges between them that try to give us an explanation of how a model does a task. The core idea behind my paper is that circuits are useful abstractions because they're faithful, right? A faithful circuit should behave like the whole model. So if I give my circuit an input and I give the same one to the whole model, the output should be the same. However, when we're evaluating circuit finding techniques or comparing two circuits, it's actually pretty common to just look at overlap instead. For example, you might evaluate your circuit finding technique by finding a circuit for a task, comparing it to a known circuit in terms of how many nodes or edges overlap, and if there's a lot, you say, well, they're the same circuit. Or similarly, if you have a circuit for one task and a circuit for another, you might say that they're the same circuit just based on their node or edge overlap. And so the question that I'm interested in answering is, are these two things the same? Can we use overlap sort of as a proxy for faithfulness? And the answer, the conclusion we come to is actually no. So we find that actually circuit finding methods that find high overlap circuits might not always be finding you faithful ones. So what we do is we introduce a new method, and we're going to compare across many different tasks and baselines to prove that in fact they're not the same. And we also find that circuit similarity, as measured by overlap metrics, differs really strongly from when we measure faithfulness. So if you're interested in questions like this, about how we compare circuits and how do we determine if the model is using the same mechanisms for one thing as opposed to the other, come over to my poster, which is over there.
All right, so hopefully round two goes a bit better this time. I'm Jacob, this is Phil, and let's talk about transcoders. Oh, nice, right slides. So yeah, SAEs, people might be familiar. They're useful for finding interpretable features, but the problem with them is that when you want to do circuit analysis with them, things get a bit tricky. And in particular, this is because you can't really do weight-space analysis where you multiply matrices, and it's also harder to decompose attributions into like a local component and a global component. So to address, the culprit of this is nonlinear MLP sublayers. So yeah, not fun, but the solution is something that we call transcoders. Other people have called them by different names before us. They're a previously proposed extension of SAEs, where essentially what you're doing is you're replacing an MLP sublayer with a wider MLP sublayer that's more sparsely activating and has interpretable features or neurons. But the thing is, even though they've been previously proposed, until now, they have never been properly evaluated or used in circuit analysis.
Yeah, so the first thing you'd probably want to verify with something like transcoders is, are you losing anything compared to SAEs? So we did both a human interpretability comparison and a quantitative comparison of the Pareto frontiers of the loss with the transcoder switched in versus the sparsity, and we found that they are approximately as good or even maybe a little bit better than comparable SAEs wherever we tested them. But the really interesting thing, the thing that makes it useful, is that if you write out the attribution of an early layer transcoder feature onto a later layer transcoder feature, it actually factorizes into this nice input invariant component here on the right. Like you can just read this purely off of the transcoder weight matrices, and then the input dependent component is basically just a function of the activations when you run this transcoder on the prompt. We show a number of other results with this. So on the left, we have a couple of case studies that we did where we basically tried to understand what a transcoder feature was looking at without ever actually reading the prompts that were making it activate. And on the right, we have one of the figures from our analysis of the greater than circuit. So how does a model know how to predict that years are in the future on the basis of like a prompt like from blank to blank. So yeah, come find our poster. It's right over there. Thank you very much.
Awesome. Thanks so much to all of our great Spotlight speakers. People join me in a final round of applause. Woo! All right. We have like 40-something posters. You can see the other 40-something posters later on this afternoon. General point on poster session norms for people who haven't been to one before. The point of this is just to learn about the work. If you really liked a paper and want to ask a bunch of detailed questions, this is your chance to talk to the authors. If the graphic looks cool and you have no idea what it's about, this is your chance to just ask a bunch of dumb questions. People are generally very flattered when you show interest in their work. Just go chat. And also, go chat with the people who haven't just spoken about their work, but have still done awesome research. Some logistical things. So we're running a little bit behind schedule, but I think we're going to make the poster session a little bit shorter and start the panel on time at 12 p.m., which will be moderated by the fabulous and one and only Max Tegmark, who I can't actually see right now, and have Arthur Conmy from Google DeepMind, Stella Biderman from Eleuther, Naomi Saphra from Harvard, and Atticus Geiger from the newly founded Prayer Group. And there'll be an hour for lunch from 1 to 2. Though lunch officially starts at 12:30 if you decide you've had too much of listening to people talk and want to step out of bed early. And we're going to reconvene at 2 for the next round of spotlights. And yeah, am I forgetting any announcements? Yeah. Mm-hmm. Yep, yeah, if you don't have space for your posters, come chat with one of the organizers. There's some coffee outside. Oh yeah, and we have t-shirts. Sadly, this workshop is more popular than our t-shirt budget, and this means there are more people here than there are t-shirts. So our solution to this is basically, for the next 5 minutes, only people who've spoken or were on one of the Spotlight or oral papers can get t-shirts. After that, it's free. It's a free-for-all. Come grab them. And there'll be some left over for the social tonight if you didn't manage to grab one here. But yeah, go forth and enjoy the posters.
and go take a seat. And if the organizers, my fellow organizers, could just quickly walk along the posters and remind everybody that they're interrupting the speakers, that would be really great. So, all right, let's start. I'm Max Tegmark from MIT. It's a great honor and pleasure to get to moderate this panel. We have really been drinking from the fire hose this morning, I feel. It was so much fascinating information. And frankly, the archive has been feeling that way recently also, with so much going on in Mechinterp. So our main goal with this panel is first to do some digesting of what's been happening during the morning and more broadly in the field of Mechinterp. Where are we? What are the biggest gaps? What are exciting directions that we need, things we need to sort out? And then towards the end of the panel, segue more towards the future. So we're going to start here, without further ado, with me asking you to each give just a very brief introduction. Just tell us your name, where you're at, and maybe 1 minute or so about which areas of Mechinterp you're most on fire about.
Hello, my name is Stella Biderman. I'm the executive director of EleutherAI. We're a nonprofit that does large-scale AI research and does a lot of interpretability research. The area that I'm most excited about is bringing kind of these interpretability tools and features and things that we're finding and combining that with learning dynamics research. And kind of my passion area is I want to understand not just, post hoc, what are the properties of models, how do we explain the behaviors of models, but how do we explain how they arise and where they come from, which I think is best done by looking at the evolution of these interpretability projects over the course of training, and then trying to turn that into practical tools for people who build models. So if you want to build a model and you want to know ahead of time it's going to have a certain property, you want to test the model as it's training and make sure that it's going to behave in a way that you want. Like my end goal from a lot of the interpretability work I do is I want to build tools that will enable people to have more confidence in how their models are going to behave before they finish spending their $2 million budget or whatever it is.
Great. Atticus.
Hi, I'm Atticus Geiger. I'm currently at a small nonprofit research lab prayer group that I lead. And what I'm most excited about interpretability right now is, I think, evaluations and benchmark is one thing, which is establishing actual goalposts for what our methods are supposed to do. And then the other avenue I'm interested in is sort of scaling up supervised interpretability methods using counterfactual data to localize concepts and trying to build a system that's sort of more general purpose and able to do that.
Naomi.
Hi, Naomi. I am a research fellow at the Kempner Institute for the Study of Natural and Artificial Intelligence at Harvard University, who have requested that we use the full name until people know what it is. And I work broadly, I would say my interests are sort of centered around training dynamics and interpretability intersection. But I sometimes sort of stray into just interpretability and just training dynamics, and am particularly interested right now in scientific understanding and interdisciplinary work where we can actually provide scientists with tools to post hoc analyze proxies for their natural phenomena and distributions.
Arthur.
Hi, I'm Arthur Conmy. I'm a research engineer at Google DeepMind. I work on mechanistic interpretability as part of the wider safety and alignment team. Recently, I've been thinking a lot about sparse autoencoders, and in particular, how we can use them for real-world tasks and to work towards that goal. This week, our team at DeepMind will be releasing open source sparse autoencoders for all layers in the Gemma 2 9B model. And we're pretty excited about that work being used by both us and the external world to try and improve our ability to get sparse autoencoders to do stuff.
Fantastic. Thank you so much. So I remember feeling a couple of years ago that Mechinterp was still way too fragmented and to be something you could call a field. And I've been really delighted to see how that's changing, how there are now actual conferences and workshops actually on Mechinterp, this thing people can mention and so on. But for something to be a field, it requires more than that just people show up at meetings, right? It requires that the people who are in it actually have a shared understanding of the big picture. So I thought we could start a little bit there in the questions we'll discuss. For example, it's been pretty popular to say for a long time that we have no clue how these black box large neural networks work. But clearly, that's grossly oversimplified at this point. We have there's been a lot of progress on how knowledge is represented in LLMs, for example. We've had many wonderful presentations about sparse autoencoders and other things this morning. We heard from David Bao how it's perhaps helpful to separate knowledge into the concepts and how they're represented, and then the relationships between those concepts. There's also been a ton of progress, of course, on the computations done with that knowledge of various types. So maybe we could make another pass in the same order that you just went through. And if each of you can just give us just your very brief take on kind of where we are. What are the main things you feel we now do understand? What are the main things you feel we now don't understand?
So I wanna kick us off by talking about some of the things we don't understand, and I think that for the philosophy of science people out there, like I would definitely describe this field as like very pre-paradigmatic. That's a tongue twister to say. We don't have unified agreement on goals, on evaluation metrics. I'm sure we're going to spend a lot of time talking about this. But one of the like really key things is that our methodologies are extremely in flux. The tools that we're using are very in flux. The standards of evidence that we hold ourselves to are very in flux. You often have papers that represent themselves as doing roughly the same thing, holding themselves to very different standards or using different methods to evaluate their evidence. And there are scientific issues with this. There are reproducibility issues with this. My team had a paper at the main conference about this, where there was a wonderful, very interesting paper about grokking with circuits for grokking with and explaining the behaviors of models trained on group operations, and built on called a toy model of universality, and it was a very, very good paper. It used slightly different standards than and slightly less rigorous standards than previous work in kind of the same area. And our paper was basically about the fact that we had tried to build on it and found results that were consistent with it. And then we went back and looked at it some more. We've realized that their explanations are fully supported by their evidence, but there are other explanations for the behavior that are also fully consistent with their evidence. And we dig into this, and we find out that all of their experiments confirm their hypothesis. There are other experiments they could have run that would have disconfirmed their hypothesis. And we present a different story about how the models this very same models that they train perform behaviors. And I think that if we spent more time reproducing each other's work and trying to individually analyze the same things, we'd see this a lot. And the paper has a lot of focus on like takeaways in terms of standards of evidence and how we should think about how confident we are in our results. And I think this is something that we need to, as a community, like spend a lot of time thinking about and talking about when we look at each other's papers. Ask people why they chose the experiments they did, why they chose the standards of evidence that they did, because we need to come to like a community consensus about what is a high enough quality of evidence to be able to really make substantial progress.
Thanks, Stella. Atticus, before you lead off, just to spice up what you said a little bit here, you gave some good tough love to the field here, right? And that tough love reminded me very much of tough love that I remember Stuart Russell gave very many years ago to the whole field of machine learning, saying that we need to have benchmarks, we need to agree on what the goals are and have things testable, comparable, etc. So Atticus, maybe you can, in addition to saying other things about what we do and don't know, comment on this too. Are there particular benchmarks or standards or metrics that you think we need?
Yeah, I would say I'm pretty largely in agreement with everything that Stella just said. I think we're definitely in the throes of trying to figure out what sort of robust evaluations look like and what hypothesis testing looks like. And, that links into one of the orals that we had earlier this morning, specifically about circuit hypothesis testing. Yeah, and I think part of having a unified view on evaluations is having benchmarks that we agree are going to be a good standard of evidence for showing a method is able to do interpretability analysis. Yeah, and that's something I'm currently working on. Recently made an interpretability benchmark on disentangling concepts. And basically the idea was we wanted to be able to evaluate a variety of sort of featureization methods like sparse autoencoders or like rotation matrices learned through, say, like PCA or distributed alignment search, a method I have. So yeah, that's something I'm very invested in personally, is trying to shore up the evaluations. But I guess on what we do know, to be a little more optimistic, is I think a lot of people have been repeating the line for a long time that we have no idea what's going on in neural networks. And I think we are starting to crack into the black box somewhat. And I think we're starting to see like some sort of like successful categorizations of what attention heads do, even on, very specific distributions of data. But, that is a starting point. And I think, views like, say, like Gary Marcus has, where he's like, there's no structure at all inside of these things. I think the most extreme versions of those views have been firmly refuted by the results we have in this field, which is, I think, something we should definitely celebrate while we're still working towards getting a sort of unified view of evaluations.
Great. Naomi?
I think we've certainly gotten better at pointing to a subset of a set of parameters that have been trained already and saying, okay, I found, the cat neuron. This is like the first example. If you've been around for a decade, no. But it's very much that we don't know which of these behaviors are caused by what decisions about the model. What is architectural? What is about the data work involved? What is about the fact that around training, like step, 500,000, they had to restart because they had a loss spike. And this is in large part because language models right now are developed in proprietary ways in for-profit companies usually, and they are not transparent for the most part. Like everyone probably saw the logs from the training of Llama way back. Yeah, but it's unusual, I would say, for companies to be fully transparent about the process. And so it becomes incredibly difficult to say, okay, under what conditions, for instance, does a privileged basis actually emerge? Which is key to why structured autoencoders work. So, or I would say so. Would you agree? Yeah. Okay. Yeah. So I would say that we need to take seriously what decisions are being made in the training of the models and what interpretability methods are enabled by those decisions specifically.
Arthur?
Yeah, I guess maybe to come back to something Stella was saying about maybe a dynamic where like one paper in Mechinterp will make a claim and then like another paper will like interpret that evidence in a different way. I think one version of this, which is like a very healthy dynamic, and to look back on like some of the like talks and stuff from this morning, I like really liked was maybe some work from like Martin Wattenberg, and there's also like a recent paper called Not All Features Are Linear, which I think I can see the author in the front row. And I think this work is like great, where it's like a type of work which looks at like a research direction like sparse autoencoders, which like very much relies on there being kind of linear representations in models, and kind of like questions that and says like, is that always true? And like I think Martin Wattenberg work like points out that like, is a bag of features really enough to like express what's really going on in these models? And I think this dynamic of like people pushing ahead with the research direction and then other people pointing out the kind of limitations of that research direction, this goes back a long way to like a paper from like maybe the last generation of like interpretability called An Interpretability Illusion for BERT, And like finding these interpretability illusions, I think is like crucial as part of like a healthy research field to not just be like blindly charging ahead, assuming that everything's working, but to like pointing out what's like the current like kind of limitations and bottlenecks of like our progress. And like I really enjoy like reading those papers.
Fantastic.
Yeah, I just want to say a couple of things to build off of that, which is, I mean, first of all, that literature, from 2019, 2020, extremely good. Undercited nowadays, just going to throw that out there. There's a lot of stuff that builds off of the work that was done on BERT several years ago that I feel kind of gets underappreciated. But what I wanted to say was that I think one of the big reasons why we have this interpretability illusion is that people have things that they are looking for, like circuits, things they want to build, like sparse autoencoders, linear representations, and they take this to be the ends of interpretability as a research field, that the goal of interpretability is to produce stuff like this. And I don't think that's really correct or should not be correct. The goal of interpretability should be to produce things that improve our understanding, and things like sparse autoencoders, things like understanding the linear representation of features. These are tools that accomplish these ends, but oftentimes they're not evaluated or not studied in the context of how much does this enable me to do something that people previously cared about, or that people outside of interpretability care about. How does it help me actually explain things and make progress on that front?
Just to add a follow-up question based on what you said there, Stella. In terms of the goals of MechInterp, there are many reasons you might be in the room, many reasons you might be interested in MechInterp. Some obvious ones are, A, you're just really curious about how stuff works. That's the same reason why many people, one of the main reasons people also study the human brain. Hey, cool system, doing nifty stuff. How does it work? Another reason, of course, is we might want to be able to assess the trustworthiness and reliability of a neural network. A more ambitious thing in that practical vein is to not just assess and quantify the trustworthiness, but improve it. To do that, we usually have to understand it a little bit better. And the ultimate, if you want to be really ambitious, is to fully understand how it works. So you can see this is the knowledge that this system has learned, this is the algorithms it's discovered, and to prove that you've understood it, if you've really figured out, maybe code the whole thing up in C++ or Python or something like that. Feynman used to joke that you only understand things fully if you can build them, right? So I'm curious to throw this back as a question. In terms of these three ambition levels, quantify trustworthiness, improve trustworthiness, and get to the point where you like fully understand it. Where are we?
I think we're kind of all over the place. It depends on where exactly you want to be. I think at the end of the day, the answer is pretty low on the hierarchy. There's a lot of papers that I think have been making good progress on this front. One additional goal I kind of want to throw out that is maybe at your second level or at your third level, maybe off to the side a little bit, is like improving, when in most fields of science, you know that you have a real understanding of what's going on when you can predict the future. Why do we trust our theories of physics? Because they tell us what's going to happen in 5 minutes. And they do it very reliably, and we're able to run experiments and use the theory to come up with explanations of the world that will tell us what will happen before it happens. And, that is, I think, something that's worth striving for in this field. That's like why I am so interested in learning dynamics, like I mentioned earlier, and trying to explain how a model is going to develop and how a model is going to behave before it's trained. But there has been some progress in that direction. I've written several papers on this topic, but it's definitely very, very nascent. And I think in general we're at like the lowest level of the hierarchy that you mentioned.
Great. Anyone else want to take a swing at this as well? Atticus?
Sure. Yeah, sure. Yeah, I agree. I think we're at a pretty low part of this hierarchy, all things considered. And yeah, I think you talk about prediction as being sort of like fundamentally linked in with how what understanding is. I also think a crucial word there is control as well, where I think what we really want from a lot of our interpretability sort of like explanations is
either the ability to, not just the ability to control the model, but also understanding how the model controls itself. And there I would sort of differ between like activation steering as like a method, like we're injecting things in to try to control the network, versus something like activation patching, where we're really staying on the distribution of network representations, but we're trying to see how is this network in fact controlling itself and sort of manipulating its own little like knobs and controllers. Yeah, I think I'll just leave it at that. I think we're really baby steps on this problem.
Yeah, I think fundamentally skeptical of the idea that interpretability gets us like any of the way there, really, in terms of guarantees, which seems to be the main thing that we're talking about when we're talking about trustworthiness and what we need here. Guarantees are repeatedly shown to be very brittle, I would say. The model tends to learn around any kind of intervention you try to impose, or the redundant features allow it to circumvent whatever circuit you manage to intervene on. And I'm not convinced that any current work has seriously addressed this problem, which we've known about since, like, I don't know, like what year? Like it's pre-COVID research. Yoav Goldberg's group did work on this, like probably in 2018 or something. It's like we've known about this problem and nobody has managed to really seriously address it.
Yeah, on Max's question, I would agree that like I'm kind of like somewhat pessimistic about making guarantees about what models are doing with mechanistic interpretability. But in terms of like the other two levels of like, can we like kind of like assess or like audit models for like trustworthiness, and then also can we like improve the trustworthiness of models with interpretability? Of those two levels, I'd say we're like probably at one at this point. Like an example which comes to mind would be like you can like audit models with like the trained sleeper agents, which is from like an Anthropic paper where they have like an update, and you can like kind of detect the sleeper agent with like a simple linear probe. So there are like very simple techniques which can like do that, in my opinion, by using like the internals of models. And then I still don't think we've reached like the second step. So like actually like using this for like making models like safer in practice. And I think the reason there is like probably mostly a question of competitivity. Like if you have some like knowledge or like some ability to audit your models, you should be able to immediately turn that into a method that can like make them safer in practice or whatever. I think that like the actual blocker in practice is that people have generally chosen like simpler methods, just like doing safety training or whatever, than actually doing the mechanistic interpretability work, because often mechanistic interpretability is like considerably harder and like a pain to make work on big models. And so like I'm like pretty like interested in work at the moment that like pushes on like going from that like kind of step 1 to step 2, would be my opinion about like where we're at and like where we should be pushing for.
Great. So staying on this broader question of where are we now, what do we understand, and what don't we? If we circle back to what David Bao was talking about, you know, knowledge versus computations, for a moment here, I'm very curious what you think about if you look at Llama 3405B, for example. Out of those 405 billion parameters, does it make sense to, roughly speaking, talk about what percentage of that is knowledge versus algorithms, or are they inexorably blended together somehow? You know, when we first wrote our very first computer program, most of us, it was probably like really garbage programming habits, where right in the middle of the program we would put I equals 5 or something, and kind of mixing together data with algorithm, right? And then later we got a little older and we were scolded, did not do that. If you have a very large data set, I'll put it in an SQL database and so on. And for many large human code bases, like if you were to actually try to write a Python code to translate German into Italian or something, most of it would probably be database. And you would have much fewer lines of code. So I'm curious, do you suspect that it might be similar for LLMs, that there's a vast amount of knowledge that if we could just figure out how it's stored, we could put it in a database and then have a much smaller model that's actually doing all the magic algorithms? Or do you think most of it really is algorithms, or that it's just hopeless to ever separate them?
Yeah, that's a good prompt. I think my perspective, maybe like the sparse autoencoder perspective, is that like we can find like a huge number of features inside these models, which would be roughly like the knowledge the models have. And so I think we're like improving on that, and it's not perfect now, but that's a pretty good frame for like getting quite a lot at like what knowledge the model has. And I'd be curious if anyone like disagrees with that perspective. And then like now we need to be pushing more on like figuring out what the algorithms are that kind of join up these kind of like bits of knowledge in the model. And I don't think we've like pushed the limits of like what algorithms these models can implement at this point in time.
Yeah, in terms of, let's say, knowledge versus algorithms, I think that we have now substantial evidence. I mean, like you won't catch me taking an unqualified position on this, but because like what? Yeah. Well, I mean, clearly there's overlap. There's what in evolutionary biology is called pre-adaptation, where features can be reused for a different purpose, for sure, like later on when the model is developing. But I think we have also seen strong evidence of distinct subnetworks and circuits within a model, and models that have a clear sort of difference between memorization and algorithmic behavior. And I'm going to specifically point to Stephanie Chan's work on in-context learning recently, which showed that in-context learning and in-weights learning can be differentiated, and that there is a point where the model that is trained in an ambiguous setting will transition between those two different sort of strategies. Shakarmurti at Stanford put out a paper that showed that language models that are trained in cases where the grammatical rules are ambiguous switch grammatical rules at a specific point in training where they learn that syntax is generally hierarchical. And then there's been a fair amount of work, including some work by like Will Merrill and Nikosh Tivilis. I mean, I'm like giving names so you can look these up, but I think they are all very strong evidence that we can identify circuits that compete with each other at specific stages, and that differentiate between memorization, generalization, linear, hierarchical, in context, in weights. And so I think it is very real that these are differentiable.
Right.
I don't think I have too much to add, but I think maybe a distinction worth making when Arthur talked about like the features of sparse autoencoders being like the knowledge of the model, and connecting that with sort of like in-weight learning versus in-context learning, that there's something more like, like the working memory of the model as, you give it like an addition problem it's never seen before. It's not relying on external knowledge in some sort of way. But then like, what sport does Michael Jordan play, for instance, is something that it might just have stored in its weight. So that's just a distinction, I think, to keep in mind. But I'll keep it at that.
So one thing I want to talk about is how there's a lot of good and growing tooling to kind of say this distinction, the in-weights versus in-context learning stuff that Naomi was talking about. I find that literature is like really, really fascinating, really, really high quality. I was actually talking about this yesterday. I was on Twitter, and so there's a paper about how model performance will improve with in-context learning, even if the demonstrations are wrong. And someone tweeted this paper. This paper came out like a year or two ago, I think. But someone tweeted this paper and was like, "Why? How does this make any sense?" And I just quickly responded like, "Because in-context examples are not there to teach the model new facts. They're in there to tell the model what it's actually supposed to be doing, what the pattern input-output pattern looks like." And this is something that I think is really important to spend more time as a field kind of thinking about, especially when it comes to the way that we design our evaluation metrics for knowledge, because it's very often the case that model will know a piece, or a model, I want to avoid saying no for reasons I hope will become clear in a moment. A model will be able to use a piece of information in one context and not be able to use that same piece of information in another context. And so, we have evaluation benchmarks that we take to be, highly representative of the ability to, whether it's like an embedding, whether it's like a probe of some sort, or whether it's like a QA benchmark that we often take to be measuring whether or not a model knows something. There's a lot more nuance there going on. I want to tell a story from a paper that's going to be, or I guess an update to a paper that's going to be coming out probably next month, where we are looking at how different prompts influence the ability of a model to answer factual multiple choice QA problems. And one prompting style that's become very popular recently is the one that's used in the MMLU paper by Dan Hendricks et al. And it is very good for a lot of models. It is horrible for any model I've ever trained. And it's really hard to describe just how utterly destructive to the ability to answer any questions it is. So if you take the MMLU style prompts, and so I trained a 20 billion parameter model in 2021 called GTB NeoX 20B, and not only does it get like very poor grades on MMLU, but if you take something that's very, very easy, like say ArcEasy, and format it via the MMLU QA format, performance goes to random. And this, I assume, is a direct consequence of some facts about the training data that I don't understand yet. But if you use the standard ARC evaluation setup, the model performs, pretty much exactly how you would expect based on the number of parameters and the number of tokens. But when you use the MMLU formatting specifically, like literally performance goes from, I think it's like in the 80s to random, which is really, really wild, and something that I think people need to think more seriously about when talking about benchmarks for measuring knowledge and transitioning from trying to say abstractly like, oh, the model knows X, and kind of turn that into, oh, the model's able to leverage this information in this particular context. One other quick example I want to give of this is that we've gotten, with RLHF, we've gotten DPO, we've gotten very good at training models to be less overtly racist or discriminatory and such. There's several very good applied papers that have come out recently that say that all of the, most of the line commercial APIs do horrible things or recommend horrible things that their designers certainly don't desire in the actual applied context. So there's a paper by some medical researchers at Stanford who use it for medical QA, and they find that it regularly recommends stuff based in eugenicist medicine for care for Black people. Naomi has emotions about what I'm saying.
Cool. Yeah. Just what I'm. Good. Why don't you do a quick comment, and then I want to move on, because we also want to leave some time for the audience to ask tough questions.
I think this is sort of a let's say an artifact of the way that we do evaluation being totally disconnected from any actual deployment setting. And what we actually need as a field, we just released a position paper on this. I'm just going to, people who are interested in evaluation should look it up. Is we need an actual discipline that's sort of more like pen testing and security, because that rather than sort of within the ecosystem and incentives of machine learning research to do that kind of practical evaluation for deployment, because we need dynamic evaluations and we need people who seriously know what can happen in the wild in practice to develop custom evaluations before deployment.
Great. Thanks, Naomi. So Stella, when you started talking about a particular area related to in-context learning that would be great for people to work on, that was a perfect segue into what we're going to do now. So we've talked a lot about where we are, what we know, what we don't know. And before we open it up to audience questions, I want to ask you some questions about where you would really like us to go next, what you see as very promising future directions, maybe future directions that you feel are undervalued, too ignored, despite their potential. And in particular, since you're also saying we should be clear on why we're doing it, if it's something which is mainly, if you can, tell us whether we should do this mainly because of curiosity, it's cool to understand stuff, or whether you think it helps with safety and trust somehow, or whether you feel the main reason to do it is just that it increases somehow the power of the networks. So who wants to make some wishes first, or calls to action?
So I want to quickly say that Naomi was the person who was talking about that, not me.
No, but you also said one area that would be great to work on is. So
no,
I just want to commend you on the segue.
But I'll take the question of what do I want people to work on. So I'm gonna plug my personal research agenda here. It's great to have this opportunity because I was feeling ill yesterday and I missed an oral where I was basically going to plug my research agenda for for 45 minutes. So I'll do that now. What I really want people to work on is I want people to work towards building tools that will enable us to deliberately design models that have properties that we want. Which is kind of vague. So to give like a specific example, there's a lot of stuff about information elicitation and memorization that's been happening that's very, very interesting. But from the perspective of someone who's building an AI system, the percentage of text that is memorized is not like a very valuable thing to know. What you care about is the memorization of specific data points, and you would like to be able to know before you finish training whether or not copyrighted books get memorized by your model. And so tools that enable you to evaluate smaller models or evaluate early in training and make predictions, with confidence bars and error bars certainly, but make like predictions about how often copyrighted books versus other kinds of text are going to get memorized is a really essential tool to put in people's hands so that they can proactively design models that behave more the way they want them to. I'm certainly not going to say that that's the only acceptable reason to be interested in this stuff. My background is in theoretical computer science. Doing this for the sake of doing it is very near and dear to my heart and a major part of why I'm interested. But I think that in terms of taking our work and making like a positive change in the world, I think that's one area where there's a lot of opportunity and a lot of open questions and currently very little work.
Thank you. Atticus, do you want to go next?
Yeah, sure.
Future directions.
Yeah, so I'll mention two things. So first, I think people throw around the term like basic science a lot when we're talking about interpretability. Like, yeah, we're just messing around in a sandbox to try to figure out what's going on. And I think something that ties into some things talked about earlier today by David Bao and Martin Wattenberg and Aaron Merler are just like, people have been thinking about these sorts of ideas, not just for 4 years or for 6 years, but for decades, maybe centuries in some cases for some of the more fundamental things we're talking about. And trying to sort of like shore up the theoretical foundations of what interpretability is. If you want this to be like a real science that's not pre-paradigmatic, we should be embedded in some sort of mathematical theory. People who know me will know my personal opinion is that that should be causality and also sort of causal abstraction, where we're trying to understand how to simplify a large process into a tiny process and do so faithfully. So yeah, and I just, to plug my own research, just recently released like a 40-page paper that just really goes into a lot of theory of causal abstraction related to mechanistic interpretability. And then on the other side, I think if you're not doing sparse autoencoders, which it seems like maybe 80% of people are doing sparse autoencoders right now, something I'm interested in is trying to scale up supervised interpretability methods. So if we have sort of counterfactual data, what should happen if certain concepts are under intervention? How do we use that to not just localize a single concept, but instead train a system that is able to localize a concept sort of like on demand? And I think that is a sort of like alternative, ambitious program that probably could involve sparse autoencoders. I don't really think it necessarily will, but yeah, I think those are two sort of directions that I'm personally excited about doing.
Great. Naomi?
Yeah, I was actually also about to bring up the fact that a large portion of people in interpretability right now are working with sparse autoencoders, but I would go beyond that. I would say that there is a very small number of topics that everyone has sort of managed to become funneled into, sort of like a research monoculture. And I think that as a field, we would really benefit from, I'm not going to make a specific proposal, but, turn off your computer, turn off your phone, like don't go on archive for a week, go to the woods, and bring a book about information theory, evolutionary biology, whatever, like something that isn't already like being read by everyone who's following, the same people on Twitter as you, right? So I think that everyone could go like mad hermit for a minute and then like come back and we would have so many new ideas. And here's the real pitch. You won't have to race everyone. You won't have to go, oh no, I'm working on this and I know 500 other people are working on this. Who's gonna, like you can take weekends off for a bit. You just need to work on something that everyone else isn't already working on. And I think that it would be so good for our field. And then totally orthogonal future direction that I'm the most excited about, actually. And the thing that I'm most interested in right now is, the motivation that I have personally is that we should understand things on principle in the world around us. And these models are in the world around us now. They're part of our lives. And we should understand them just on principle. I like that we do science as a species. And so I think that another thing that then is exciting is the idea of using these methods that we've been developing, especially like post hoc interpretability methods, to understand these models that are effectively acting as real proxies for natural phenomena. And there's been some work on this. Like now there's a team that's now translated one word of whale, humpback whale. It means let's go hunting. Yeah.
Great.
Yeah, that's a good question. I guess my perspective looking forward, and it might be a bit focused on maybe stuff at like Google DeepMind, but I do think it generalizes, and I'll get to that. My perspective is that like right now at like Google DeepMind, for example, like as a reality check, like mechanistic interpretability is not being used in like the safety training of these models, nor in like the kind of safeguards we apply to these models. And so I think my perspective is the field should like try and like develop like methods inspired by mechanistic interpretability to like attack like real problems related to kind of the safety training and the safeguard deployment that we like use with these models. And maybe that's a bit of like a downer note, whatever. But I think there's like some cause for hope here where like the models are just getting better. They get better every single year, every single month it seems. And so there'll just be more and more kind of like surface area and kind of like places where we need to be applying more safeguards to these models, where the alignment techniques break down. And I think there is some hope that like these kind of techniques in this field, which probably go quite a lot deeper and can hopefully be more rigorous than like other techniques in the field, and that can like be therefore like actually useful in the kind of like training stack. And I guess like to give like kind of concrete examples in cases where like I don't think this is something which is like done like or can only be done in labs at all for what it's worth, because I think there are like a number of fields such as like unlearning, such as kind of like monitoring for harmful outputs rather than just kind of like training those away, even improving safety training to ensure models have a better sense of like the kind of like responses that you're supposed to reply to and the responses you're not supposed to reply to. I think we're getting like already good like insight into that work. For example, there's a poster, Andy Arditi's work on kind of refusal being mediated by a single direction. And I think we should really be pushing on those things that get it close at like the kind of safety training and the like the guardrail deployment in these models. And yeah, I think that like to emphasize, this is not something that's just for the labs, though like we would use those techniques if they were out there in archive, and I hope that does happen in future. That like all these like white box style methods are kind of prototyped on the small models. Like it's just like really hard to use the big models, and they're a pain. And we like generally have a lot of like techniques which have transferred pretty well from the small to the big models or whatever. So I think it's like very important that we kind of like benchmark these kind of real world tasks, and we develop methods that work for these real world tasks on the small models, and then that might actually be part of kind of like the next generation of kind of like safety training and like guardrail deployments. And I think that like that for me is like what the best direction to push on going forward. And as mentioned, there's already work going in this direction, though like I don't think we're at that point yet. And so like I'm really interested in pushing on that.
Great. So in a few minutes, we're going to take audience questions. So if you have questions, please line up in the middle aisle here behind the microphone, which is right near where the camera is. And to give you time to go line up there, I'm going to throw out one last question to our esteemed panel, inspired by Naomi, who encouraged us to think, if not in the forest, at least outside of the box. If we had been at a conference like this in, say, 1947, there would have been a big section on vacuum tubes, and everybody would be like, yeah, vacuum tubes, vacuum tubes. What about vacuum tubes? How can we make them a little bit better? Blah, 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 you know. And if you had it maybe 1955, a year after the invention of Fortran, people would have been so stuck in the idea that it's the von Neumann architecture that's going to get us all the way to AGI. They would have been quite perplexed that we're talking about neural networks here. And I can't help wonder if Naomi is very right about her suggestions here, because so many people, especially younger people in our field, seem to put an equal sign between AI now and neural networks. And some even put an equal sign between AI and transformers. And most of the wonderful work here is on transformers. So, wild Naomi-inspired question to all of you. Do you think do you have any thoughts about different architectures altogether that might be helpful for MechInterp? Any suggestions for people, things to think about, mess with, try?
So I have two quick replies to that. One of them is that I think there's absolutely a lot of space to be doing novel architecture research. I think that the idea of designing architectures that are more interpretable, that can be operationalized to obtain more interpretable results is really great. I mean, that's the motivating impetus behind SAEs. It's supposed to be a model that behaves like the other model, but is more interpretable. On the bit about equating things with transformers, I mean, that's something as a large language model trainer do all the time and try to do less of. But there is growing interest, I think, in the interpretability field. I saw a paper here today about interpretability of Mamba, and I saw a paper here, and I think there's a paper in the second session about interpretability of RWKV. For those of you not familiar, these are two non-transformer architectures that get similar performance to transformers in many contexts, and I think that's really great. My lab recently has a paper about transferring MechInterp methodologies that were designed specifically for transformers to alternative architectures, and I think the message of this paper is mostly positive. It is these things that we developed overfit to transformers do in fact can be easily adapted to other architectures, and you get kind of similar results. And so I think there's a lot of reason to be hopeful, but I do think it's something that's important for people to think about and pay attention to in their work.
Cool. I mean, and just for optimism, it's important to remember also that like Naomi's brain uses about 1,000 times less power than a transformer for answering questions. And there are some interesting physics calculations showing that we still have about 20 orders of magnitude to go until we bump into any hard limits. So I'll be very shocked if 10 years from now, the best we have is transformers. Well, we have a lot of people who have lined up here. We have 13 minutes left. So to make sure that we can get as many of you in as possible into the conversation, I'm going to ask you who ask questions to really make sure that what you say is a question and only a question, and try to keep it brief. And I think to make it even more easy for all of you to get in, is maybe we'll take 3 of you in all together, and then the panel can respond to whichever subset they want.
We were charged about $177 for an extra microphone, so please come up and ask questions.
All right.
Yep. So there seem to be 2 parallel avenues. One is the post-hoc interpretability versus the other is trying to understand the dynamics with different levels of rigor. So what approaches do you recommend for linking these 2 fields?
Great. That's the first question, and we'll take 2 more.
Hey, yeah. I wanted to know what your thoughts were on how important it is to be doing interpretability research on the largest models, and how much value can you get from training on smaller or toy models, or the 2B versus the 405B.
And the third one.
Thanks. One of the main goals of MechInterp is providing good explanations of neural networks and behavior that everyone can agree on, but then people disagree about what counts as a good explanation, even in the philosophy of science. And 2 criteria that people might have is good explanation is one that's neatly human interpretable, and that's in the name of MechInterp itself, right? And another one would be it's a faithful explanation that's actually faithful to the causal structure of the network. And sometimes there might be a tension between these 2 things. When you optimize for neatly human interpretable explanations, for example, sometimes with SAEs, we run into that. You've mentioned interpretability illusions. We might do that at the cost of faithfulness. So I'm wondering what your thoughts are on that.
All right. So did you want to start off there, Naomi? You had your hand up.
Yeah, okay. I have, for the first 2 questions, I think. First off, scale is such an important thing. I think it's important to understand things that happen at a small scale, and it's important to understand like phase transitions and things that have we need like scaling laws for interpretability, right? Something like superposition only emerges at a certain scale, for instance. And so the methods that are specifically developed to handle that situation are particular to large-scale networks. So absolutely. And then there's a million other things that affect what happens in your network and what's an appropriate method. Things like, are you doing multipass or are you doing online? Are you doing one epoch or many, right? There are so many factors, but I think it is 100% a good thing that people are developing methods on small networks as well as on large networks, sort of like natively, because there's a lot of transfer that can go on there. And then in terms of linking training dynamics and post hoc, I think that there's been definitely advancement in that. I think we've now been seeing more and more evidence that there are artifacts that emerge from training that are still visible at the end of training. There is sort of a pruning stage, but you still end up, even whenever you look at your model, it's likely that there will be some features that are even maybe vestigial or that have been shaped by their interaction with the like original heuristics that developed at the very beginning of training. And so absolutely, like, I think that there's ongoing, it's one of the most exciting areas right now.
Great. Anyone, Atticus or Arthur?
Sorry about that. Yeah, as a quick answer to the third question, I think that's a very good point that like, actually evaluating like whether we have a good explanation of a model behavior is really hard. And so I guess maybe to come back to I think something Stella said earlier, I think this is a means-ends confusion point where like I think we're kind of all here, like we're doing mechanistic interpretability because we have some like belief in this kind of means of like getting out human like understandable explanations for our models. But we shouldn't really like think of that as the only goal we have here. And I think that some of this kind of difficulty of like even like putting a number on like the human interpretability of like our explanations confuses the fact that really from that we want to have something that allows us to do with models. We want to have something that we can improve since we have an understanding of it. So I guess, sorry if it sidesteps your question a bit, but I'm like 100% agree. It's really a worry in the field, but I think to me that seems a means-end confusion when that's kind of the goal of work.
Great. Since we're doing the many-to-many, make sure you very briefly summarize also the question before you answer it rather than just saying, oh, the second question.
Yeah, so
just for those who haven't had as much caffeine.
Yeah, so for the doing work on small models versus like large models, I would say, especially if you're aiming at sort of like developing methodologies, that there's tons of good stuff to be done on small models. I think a lot of researchers are in the position where they can't run the 4 or 5B model, and that as long as what you're doing is trying to explore new ideas and methods, it's great. I don't know if exhaustively going through and just identifying a bunch of circuits in GPT too small is going to like push things forward hugely. For the explanation question, yeah, I mean, I completely agree with the question and what Arthur said. It's a hugely important sort of like point of discussion, and I think there's a lot of debate going on currently and some good papers coming out trying to figure out what we mean by faithfulness when we're talking about circuit explanations or like causal graph explanation of what's going on. And I'm really interested in that important work.
Stella, are you okay if we take a few more questions before you answer? Sure. Great. So I want to see if we can get everyone in. How many? We have 1, 2, 3, 4. Yeah, why don't we do all of yours? Because we only have 7 minutes left and we also need to get the answers.
Yeah, so I have a question about more of that means-end thing. So if we look at activations and weights as a sort of a modality like images, it's one that's very foreign to us. And so it's, to me, seems like a very attractive target for automation, for deep learning itself. But on the other hand, it seems like if we want to understand these models and we just outsource all of that understanding to a model, that's very unromantic. And so my question is like, how much automation should we strive for? How much do you see as acceptable? How much do you still see as understanding? Do you care whether it's a model that understands other models or that's a human?
Great, and for the rest of you, try to keep your questions really succinct. Otherwise, we're just going to have all the questions and then go for lunch without the answers.
I am interested in thoughts on how would you approach making models more interpretable, either after training or like architecturally during training?
Thanks. What would interpretability's AlphaGo moment be like? Is it worth achieving?
So Naomi, you mentioned this idea that we should, as researchers in this field, be like reading more broadly and working on things that aren't just sort of jumping on the bandwagon. This is what I've been trying to do for a few years, and I'm still resubmitting the same papers, whereas whenever I do just jump on the bandwagon, I'm much more easily able to publish. So as someone who wants to follow your advice but also wants to graduate, do you have any good advice for me?
Great.
So Naomi mentioned early on that there are no guarantees in language models, and there's always things to attack. I largely agree with this actually, but it also means that this entire enterprise, as Max mentioned about, trying to improve things, might just be a house of cards. And I wonder if you guys have thoughts on how to overcome this and what is the most promising solution.
All right, so that was definitely a lot of questions. So on the question of there was a question about what models we should be using and big versus small, and as well as questions about when designing towards what we have access to. The largest and best models are not things that we have meaningful access to, and that's just like a fact of the world that we live in. I think that if you look at the models that interpretability researchers use, there are more people doing interpretability research on Pythia than, proportionally speaking, on Pythia than on Llama, and there are more people doing it on Llama than on GTB3. And I mean, this is kind of a direct consequence of the level of access and how these computational artifacts enable people to do research. I think that it is very good for people who train models to kind of actively think about how they are going to empower people to do mechanistic interpretability research, whether this is designing more interpretable architectures to train their models with, or whether it's designing their model suites in ways that lend themselves more easily to analysis. The origin of the Pythia paper was that my colleague Haley and I sat down and we made a list of all the questions that we thought were really cool that you couldn't study with any publicly available language modeling suite. And we kind of distilled that down to a list of requirements, and then we set out to deliberately design a suite of computational tools that was going to provide that kind of support for those kinds of projects. And I think that's really valuable. I think that, there is a lot that can be done in terms of doing stuff on small scale things, whether it's because you don't have access to the weights of particularly large models, or whether it's because you only have a small GPU yourself. I think that Naomi had mentioned scaling laws for interpretability. I think that the question of how does what we analyze today generalize to larger models is really important. One kind of trap it's easy to fall into is to not just is to think about interpretability as I want to explain the properties of this specific model, and that's helpful if that model is extremely widely used. But much more generally, and I think much more scientifically interesting, is the question of what general phenomena are we able to identify, and that studying things at one scale and then exploring how they show up at other scales, or examining things in one model family and showing if they generalize to another model family is a really essential component of that. And just going to plug, my colleagues Kurt and my colleague Kurt has a paper at the second poster session where we're doing exactly that. We're looking at interpretability circuits on small models and generalizing it to big models, and we're looking at circuits early in training and generalizing it to late in training. And you should come talk about that with me and with Kurt.
Great. We have 2 minutes left, and we are the only thing standing between them and lunch now. So if you have any very brief, either final responses to questions or other final thoughts you'd like to share, this is your moment.
Yeah, I'll just target the automating interpretability question, and I'll say that just giving sort of max activating examples for neurons or features is not going to be enough to get a good automated interpretability method going. You really want to involve counterfactual data where you're doing interventions on the features and seeing what they do and certain types of interventions, and then you also need to build those evaluations in on the final part where you hold the thing accountable via some metrics you've decided on beforehand. Also, the person who is struggling publishing their work, keep doing it. I believe in you.
For that question of how to do stuff which is off the bandwagon and maybe controversial and still get a job, I have a personal strategy for that also that worked for me. I'm happy to share over lunch.
I have a personal strategy too, actually. Every paper is a position paper. Yeah. Genuinely. Every paper you write, if it's something unusual, is an argument that everyone should be thinking about this and that this is what's missing in the field. So focus on your argumentation.
All right. Super brief final comment or?
Okay, sure. There was a lot there. I guess an AlphaGo moment for interpretability for me would be we actually prevent some deployment of some model which had some extraordinarily dangerous behavior which no other method could detect. We actually had a win for we looked in the insides of the model, we found something that the model was doing which was misaligned or whatever, and we stopped that from happening because most of the other systems we have are very kind of black box, input output pairs, behavioral evals, and to have some kind of ability to do something that we otherwise could not do with any other method that's out there would be an AlphaGo moment for interpretability. interpretability for me, at least.
Great. And with that, I would like to let's thank our wonderful panel. Thank you so much. It's really great. And before you head out here, we have some final practical words from Kayo.
Yeah, just a few brief announcements before I let you all go for lunch. So first, we have an evening social at 6:30. Sign up is still open. So we will close signups at 2:35. The link to sign up is on our website, and we will send out decisions by 5 p.m., around 5 p.m. Second thing, Spotlight is back at 2 p.m., so it would be great if everyone can make it back here. And for speakers at the Spotlight session, please be here at 1:50. And then those of you who have posters in the room, we have another poster session coming up, so please take the posters down during lunch slot. Thank you. Have a great lunch.
Start, and we'll just, if you see people coming in sitting next to you, remind them about the posters, because again, I will start going through and naming people. All right, so thanks for coming to the Spotlight session 2 for our second poster session. It's, well, each person will have 2 minutes, but what's interesting is some of the speakers couldn't make it due to a combination of visa issues and other random administrative bullshit. So we have some videos that are going to be played in lieu of them coming to give a talk. So this is the first one.
Note that there will not be...
Hi, I'll briefly tell you about the paper SAEs Match Supervised Features for Steering on IOI. So the motivation is that we can train our SAEs and their features look very nice and interpretable, but how do we know they're the true features used by the model? And so far there have been a few evaluations proposed for this, but they have all been kind of indirect, and it would be very valuable if we had a more direct way to see how close SE features get to ground truth features for various downstream tasks that we might come up with. Hi, I'll briefly tell you about the paper SAEs Match Supervised Features for Steering on IOI. So the motivation is that we can train our SAEs and their features look very nice and interpretable, but how do we know they're the true features used by the model? And so far there have been a few evaluations proposed for this, but they have all been kind of indirect, and it would be very valuable if we had a more direct way to see how close SE features get to ground truth features for various downstream tasks that we might come up with. And indeed, some recent work proposed a way to do this by considering supervised SAEs that are constructed for narrow tasks by extracting some prompt attributes directly from the inputs. And in this work specifically, we focus on one of the evaluations proposed in this prior work, which is, can we use feature arithmetic over SE features in order to steer the model as successfully as the supervised SAEs can? And in a bit more detail, when we do model steering with SAEs, we want to go from a source activation, which is the original activation we want to edit, to a target activation, which is obtained by passing the edited prompt through the model. And supervised SAEs can edit by subtracting one feature from the source and adding one feature present in the target. And the question is, can unsupervised SAEs successfully edit in the same way? And we improve upon prior work by essentially evaluating over more different kinds of SAEs and using more different training tricks for SAEs. And pretty amazingly, we find that top K SAEs, in particular with k equals 3, which is exactly the number of supervised features we have in our supervised SAEs, can match supervised SAEs. So thanks for listening. Check out the paper and have a great workshop. Thank you.
All right, and we have our hello. All right, we have our first speaker who's going to present on, well, SAEs.
Woo! All right, my name is Rob Krasnowski. I'm going to be talking to you about interpreting attention layer outputs with sparse autoencoders with my collaborator Connor Kissane, supervised by Arthur Conmy and Neil Nanda. So, do they work? Yep. Do they scale? Yes, at least from GLU2L up to GPT-2 small and Gemma 2B. Are they sparse, faithful, and interpretable? Indeed, average L0 of around 20, over 80% interpretable, and they're open source. Go check it out. Scan our QR code over at the poster over there, read our paper. I trust everyone to diligently review that after this talk. All right, note that we train on the mixed values or the Hooke Z, alternatively the attention output prelinear in various parlance, not explicitly on the outprojection to the residual stream. This should be invariant up linear transformation, whatever. But this enables us to attribute back to individual attention heads. Also, key takeaway for this talk is that attention SAEs are useful tools for interpretability and circuit analysis. Go use them. Go out and use them. Why do models have multiple induction heads? We were able to answer that by noticing that there are specialized roles like long-range induction, A, B, C, D, E, short-range induction like A, B, and the widely studied IOI circuit by Wang et al. We were able to answer an open question as to how the position of names gets encoded and pulled in. For example, we found an SAE feature directly corresponding to the direction of, oh, there's a name preceding the and token, and that's what gets pulled in. Cool. We also find attention SAEs are qualitatively different from NLP SAEs and come in families, including long-range context tracking, like sentences related to pets, code, news articles, etc. Short-range context tracking, like sentences starting with which, ending with a question mark. Induction features, like board is next by induction, like whiteboard or dashboard. We also looked at the top 10 features across all 144 attention heads of GPT-2 small. So what do they look like? Let's spend the remaining spotlight seconds going through some examples. We have a hockey feature, we have an infectious diseases feature, we have a oops, let's skip that. Superhero feature, we have a beer feature, cheers. We have a feature that tends to mend up boosts women. How empowering. We have dogs, cats, and horses. We have a successor feature, 7 and follows 6. We have a Roman numeral successor feature. Cool. We have DFA onto first and activation on second. We have DFA on second, activation on third. We have an infinite family of successor. I'm just kidding. Attendance of previous year, activation on next year, election context tracking, vegetation and ecology, higher and critting. We have a gay rights feature, a diseases feature. We have a safety feature. Maybe we should just be pin steering with that always set to on. We have a spatial temporal relationship feature that tends to under, to before, to between, to after. Induction feature that copies and boosts F, M, as well as AL. And finally, a thank you feature where the top positive logic boosts are very kindly, sincerely, very immensely. So again, guys, so for go check out our paper.
Thank you to Rob for winning the prize for most words spoken in a spotlight talk. Over to Tamash. Also the most slides.
It's dense in the slide basis.
Hello.
Testing.
Hi, my name is Tomas. I'm going to be talking a little slower than the previous guy, but I hope you guys will manage. Our work is called Describe and Dissect. I want to say I'm the third author. Most of this was done by Nicholas and Rahul, who are like awesome high school students, but could not make it. So credit to them. The basic idea is we want to automatically explain individual neurons in a neural network. This could also be SAE features. It's kind of the same thing. But we want to get a natural language description of a single neuron. The way we do this, it's pretty simple in the big picture. So first we collect a set of highly activating inputs for that specific neuron. Next, we feed it through an image-to-text model. So like a blip generates captions for each of the highly activating images. Finally, we feed it through a GPT model that summarizes what is in common between all the different captions for the different images. And one cool trick we do here is like we don't only generate one description, we actually generate a bunch. And then when we have a set of these candidate concepts, we feed them through a new model, which is a text-to-image model. So we generate new images with stable diffusion, see if they still activate the original neuron based on the description. And we find which of the candidate concepts was the best one based on the new images. And it works pretty well. We get some nice descriptions for neurons. And we ran a big study on like Mechanical Turk, on like whether people agree that our descriptions actually match what the neuron is doing, at least at the highly activating inputs. And you can see they much prefer our method compared to previous ones. Thank you.
Hello. I'll be presenting Look Before You Leap. Okay, so our dream is to do scalable oversight on model internals. So to that end, we want to look at a single abstract task that we can have many instantiations of, and we want to kind of avoid doing all the manual work of sort of normal mech interp. Okay, so simple task, abstract retrieval. The most basic version of this is you have like some story in your context and you ask some question about it, like what is the city or who's the main character. In our paper, we also study translation, factual recall, variable binding, some like programming kind of tasks. Okay, so what do? We do a simple patching experiment. Some of you might know this as an interchange intervention. We take the last token vector at a single layer, and we patch it from one forward pass to another. And what we see is somewhere around the middle layers, we get this beautiful, clean thing that happens where we end up answering the question from the thing we're patching on the story of the thing we're patching to. And what's really nice is that this phenomenon turns out to happen for all the models we checked. You get this beautiful plot with Llama 70B, where initially, if you patch too early, you just like don't do anything. If you patch too late, you copy the answer. But right in the middle, there's some clean layers there where it spikes and you answer like the question from the first thing on the story from the second, and this works across all our tasks. So if you'd like to learn more, come check out our poster.
Hello, I am Samyak Jain. It's my pleasure to present about what makes and breaks safety fine-tuning a mechanistic study. So synthetic setups are cool, right? We propose a synthetic setup, and we want to understand these two questions. How does delta W that is learned by safety fine-tuning learns a safety mechanism? And how do jailbreaking attacks are able to exploit this delta W? For this, we analyze 3 different safety fine-tuning protocols: supervised safety fine-tuning, direct preference optimization, and unlearning. So the motivation for us for proposing a synthetic setup follows that it allows us to have a fine-grained control over generation of jailbreaks, which would be difficult in a real-world setting. Nevertheless, we also validated our analysis on real-world models. So we argue that an input to an LLM can be considered as a composition of 2 components, operators and operands. So as shown here, design a cycle. So design is an operator which is operated on a cycle and results in an output. We model operators using these bijective mappings and operands using probabilistic context-free grammar. For more details on how we generate jailbreaks, please visit our poster. We first analyze how safety fine-tuning works, and we perform feature space analysis for this. We find that safety fine-tuning encourages the clustering of safe and unsafe samples, and the separation between the clusters is actually increasing when we perform stronger safety fine-tuning like DPO or unlearning. Next, we analyze how the weights updates are actually responsible for this clustering, and we observe that delta W, that is the update in the weight, is actually specialized for unsafe samples, and it projects them into the null space of the instruction fine-tuned model. And finally, we perform jailbreaks, and we observe that these jailbreaks are able to evade the processing by delta W. As a result, they behave similar to safe samples. Thanks for your attention, and come visit our poster. Thank you.
Hello. Yeah. Thank you for giving me the opportunity to present our work, decomposing and interpreting image representations via text and VITs beyond clip. So recently there has been some progress on understanding how clip VIT built this image representation by Ghandeharioun and others. So they basically exploit 2 properties of VITs. So one is that these VITs are linear in the OV circuit, which is that the final representation can be linearly decomposed exactly into direct contributions from attention heads over each token. And then the second property they use is the final representation lives in a shared image text representation space, which enables like easy interpretation via text. So our research questions are as follows. We have 2 research questions. So the first is that the contributions of these model components that are actually getting decomposed, they are not explicitly computed during the forward pass, right? So they need to be reconstructed manually using knowledge of the model architecture. So like different models have different residual transformations, like different ways of representing the final layers, and then different attention mechanisms. So can we automate this by writing a function f so that you give the image representation in components and it yields a decomposition of the image representation over components. So this is what we want. So the second thing is, okay, now we have the contributions. How do we interpret this without a text encoder? So we could train a linear layer to predict components, concepts, and then use this for interpreting the components, but this is not very flexible if your concept set is varying. So can we find a function to map the contribution vectors of each component to clip space? And then we utilize the clip text encoder to interpret these. And we do have a few cool applications like image-based image retrieval, spurious correlation mitigation, and so forth. Please visit the poster. Thank you.
Hi, so Inception v1 was the target of a lot of early mechanistic interpretability work. However, polysemantic neurons, which respond to multiple unrelated concepts, hindered progress. And this is hypothesized to be because of superposition, which I'm sure as many of you already know, is when features are represented by combinations of neurons. So a really natural question one might ask is, what if we bring this progress back to Inception v1? So I used a pretty standard sparse autoencoder and trained that on Inception v1, early vision, so the first 5 layers. And then I made 2 additional modifications to accommodate some compute constraints, which was oversampling large activations and using like training on the branches of the layer rather than the entire layer. So firstly, we see that SAUs learn new interpretable features, and a lot of the time they are more interpretable than their most similar neuron. Curve detectors are likely the most well-studied neuron family, but when you look at this work, it's apparent that some are missing. Essentially, like, you would expect a neuron that might respond to a curve orientation to exist, and it doesn't. However, if we look at the SAE features, we not only recover these original curve detectors, we discover new ones that begin to fill in these gaps, essentially. And then finally, SAEs also split polysemantic neurons into more specific monosemantic concepts. So here you can see a double curve detector that is broken down into 2, the left and right curve in that. Yeah, so my poster is the pink adjacent one over there, and I look forward to talking to you about this. Thanks.
So you might have heard that neural networks tend to be pretty degenerate, meaning they lie in broad basins of the loss landscape, where many nearby parameter configurations kind of do the same thing. And in fact, the broader the basin, the better these networks tend to generalize. And singular learning theory, you measure how broad a basin is with something called the learning coefficient, which is kind of an effective parameter count, where if your effective parameter count is lower, your network is thought to be simpler, and that it overfits less and generalizes better. Now, you could ask, well, is this learning theoretic kind of complexity the same as mechanistic complexity? Are the algorithms inside networks that have broad basins simpler algorithms? And if so, simple in what sense? Can we use this to probe for what the algorithmic structure of the model internals actually is? So we thought a bit about this and came up with some formulas that link internal complexity in models to how broad the basin in the loss landscape of the model is. A small sample, for example, the number of non-zero PCA components in your hidden activations and gradients is important. Rough qualitative summary, the fewer variables your network algorithm has internally and the less it has them interact, the broader the basin tends to be. And then you can think, maybe we take this definition of variables and try to graph out networks with them, and maybe in that form they are more understandable than looking at something like neurons. And we did that. It works kind of on toy models, not so good on LLMs. This might be related to how our formulas don't account for stuff like superposition yet. And yeah, the link between internals and learning coefficient, Bayesian broadness, is still incomplete. Thank you.
Hi everyone, our project is on unlearning factual associations of the form. Tiger Woods plays the sport of golf, model completion. So if you think about a possible model of factual recall. You have like lookup MLPs, you have like enrichment MLPs that are early, and they like take the subject and they enrich the latent stream with like a lot of information about the subject, right? And then later on, you have like extraction mechanisms that like reach into the latent stream and like format the knowledge that you actually want, like what sport they play, into like the output format that you want. And so if you want to unlearn, like you want to make the model unable to say golf, then like you can like possibly like disrupt this in two ways. First, you can like disrupt like the MLPs. You can disrupt like the orange bubble from forming, prevent like the latent knowledge from actually like forming, or you can like disrupt like the extraction mechanism, right? You like make it so that like the model can't like extract the knowledge that like it knows is there. It just can't like format it into the output. And so if you want robust unlearning, plausibly like this should like generalize. You want like your models to like not know the like Tiger Woods play golf across like a lot of different like prompt formats, across like different extraction schemes, maybe like probing. But like empirically, like models that are supposedly unlearned just like don't generalize their unlearning a lot. And possibly this is because like a lot of unlearning targets the extraction like mechanisms towards the end, where if we really want true unlearning, we should be messing with the orange bubble, right? We should like prevent the bubble from forming. We should like mess with the fact lookup MLPs. And so what if we just like target our unlearning on these MLPs? Well, if you do, you just get like really, like you just get a lot of robustness. You get like robustness to multiple choice evaluations, you get like less side effects, but then you also get robustness to like relearning and to like probing, and like some like other unlearning procedures. This is like pretty like preprint stage, but it's robust unlearning.
Hey guys. So our paper is learning and unlearning of fabricated knowledge in language models. I'm not going to talk about the unlearning part. If you're curious, come see my poster. And this was done with our wonderful colleagues at Google DeepMind. So for the learning part, we ask this fundamental question: what happens to new knowledge if it's given to large language models? And specifically, when is it forgotten, and how much does it alter or pollute kind of surrounding facts, so forgetting and hallucination? To investigate this question, we make a new small data set filled with these knowledge conflicting facts, facts which contain these nonsensical keywords put into nonsensical places. And what happens to forgetting? Lo and behold, even after another 15,000 iterations of fine-tuning, after no longer presenting these facts are still there to a large extent. And the interesting thing is, if we make versions of these facts that are not knowledge conflicting, but rather mundane or boring, in which case they still have the same keywords, but are just put into mundane locations, positions, or on the other extreme, randomized, permuted versions of those KCFs. In both cases, on both extremes, they both forget much more. Now, what about generalization? If you take a look at this knowledge conflicting fact, look at the nonsense token 79, and you can see it if you prompt it with other prompts, it hallucinates all over the place, uses these 79s for all sorts of numerical hallucinations. And the interesting thing here again is this occurs much, much less for both mundane as well as randomized versions of these facts. And so in the end, there's a Wundt curve, a sweet spot. Thank you. Come to my poster.
Good afternoon, everyone. I'm Changyan, and today I'm going to introduce what's the influence function and how the advanced sampling methods could make it work better. So first of all, influence function gives the direct estimation of how the inclusion or an exclusion of a certain data point would impact the overall model performance. It's a quite useful tool because it only uses the Hessian and the gradient value of the well-trained model parameters. So theoretically, we need to compute the Hessian value for the whole data set, but as you know, it's very computationally heavy. So conventionally, previous research used random samplers. However, to make it work better, we propose 2 advanced samplers, which are based on feature or logic. And by experiments, we proved that our sampling methods can improve the accuracy of influence function even with less time and memory. So thank you. If you're interested, please visit me.
Okay. Yeah. Hi, everyone. I'll talk about our paper, Learning Syntax Without Planting Trees, Understanding When and Why Transformers Generalize Hierarchically. Okay, it's the same slide again. Okay, so let me start by motivating the problem of hierarchical generalization using a very simple task called question formation. You are given a sentence, and the task it is to convert it into a question. We can also look at it as an auxiliary fronting problem, where you just take the auxiliary verb and move it to the beginning. The case is like 2A, where there are multiple auxiliaries present in the sentence. The way English grammar works is that we move the auxiliary, which is connected to the root verb of the sentence, which in this case is comfort. However, we can also consider a much more simpler hypothesis that you just move the first auxiliary to the beginning. That doesn't require modeling any hierarchical structure, and that also does the task well. However, if you take another sentence, it doesn't really work always. So in this case, a hierarchical and order rule gives you different outputs. So yeah, it doesn't generalize. The order rule, while works on 1 and 2, it doesn't generalize on 3. So in this paper, what we're trying to study is that if a transformer model is trained just on sentences of type 1 and 2, does it generalize according to hierarchical rule when given 3, or does it generalize according to the order rule? And this has been studied in the past, and people have shown that if you train the model for long enough, it starts to actually generalize hierarchically, which is very puzzling, right? Because there is no tree-structured bias encoded in the network. So in the paper, what we're trying to do is trying to understand why that happens. And we have 3 main contributions in our work. The first one is that the training objective, the way we train these models, act as an inductive bias for hierarchical generalization. Particularly, we find only language modeling results in such hierarchical behavior to emerge, and all the other objectives fail to show that. Not similarly, but we also find like subnetworks or circuits within the models which are consistent with both types of generalization. So even though transformers generalize hierarchically, we find subnetworks corresponding to both generalizations. And finally, yeah, so come to our poster.
Alrighty, there's one more. Oh, also there's thank you slide, by the way. There's one more talk that unfortunately the authors couldn't come for visa reasons. So hopefully we can play that now.
Hi, this is Boshi, and it's great to be here to briefly talk about our work on grokking of implicit reasoning in transformers. A lot of previous work find that LLMs nowadays, even the SOTA ones, struggle at implicit reasoning over their parametric knowledge, where the model is not allowed to explicitly verbalize the intermediate reasoning steps. This is an important skill because it is the default mode of large-scale pre-training, and fundamentally decides how well these models can acquire structured representations of knowledge and rules from data. In this work, we try to systematically study this problem by synthesizing controlled training and evaluation data and train transformers from scratch. We find that transformers are capable of learning the skill through grokking, and that there are differences in the level of generalizations that they acquire. Specifically, for the task of composition, transformers fail to generalize beyond their training distribution, while they succeed in the case of comparison. To understand these observations, we use logit lengths and activation patching to analyze the inner workings of the model throughout grokking. We find that the model finds distinct generalizing circuits for the 2 tasks, namely a sequential circuit for composition and a parallel circuit for comparison, which explains very well the different level of generalization that they acquire. By analyzing the intermediate training checkpoints, we find very plausible explanations of grokking through the lens of circuit efficiency, where the model is gradually learning the rules by reducing the amount of facts it needs to store in the weights. To showcase the power of parametric memory for complex reasoning, we create a very challenging reasoning task with an extremely large search space, and find that LLMs based on non-parametric memory fail catastrophically, while a grok transformer trained to compress and integrate all the facts to the extreme can achieve near-perfect accuracy. If you're interested, feel free to check out our paper for more details. Thanks.
All right, so that concludes our spotlights. Before we go to the next thing, I did promise that I would start shaming people who had not taken down their posters. So sorry, here I go. If I made a mistake, I apologize profusely. Let me know, I'll apologize in public, don't worry. There's a poster called On the Grokking and the Geometry of Circuit Formation by Ahmed, Randall, and Richard over there. There's a poster called Lost in the Crowd that's over there. And there's a poster called How Truncating Weights Improves Reasoning and Language Models. So if you're one of the authors of these papers and you want to keep your poster, come find me later. All right, thank you.
So up next, we have two glorious talks. I hope you're excited. We're going to have Asma talking, and then we're going to have Chris Olah talking remotely at 4:30. Asma is a senior research scientist at Google on the People in AI research team who's been doing some great work in mechanistic interpretability. Was presenting a great paper here called Patch Scopes that you should totally all go check out. And without further ado, I'll hand over.
Well, thank you so much. Thank you. Does it work? Yeah. Oh, sure. Yeah. Thank you for the kind introduction, Neil. And yeah, so I'm part of People plus AI research. Oh.
Extended screen. Yeah, can you show it? Can you show the present? Oh, okay, you see it, yeah, on the extended.
We apologize for the technical difficulties.
Sylvia. All right, can you give me the mic?
Actually, can't see it. Where is this?
Can you put up the slides up, please, Sylvia? Yeah, you see it now? Can you just, you have the, yeah, almost there. Maybe if you had the slide, yeah. I'm not very proficient in Macs, honestly, but like we just need to hit the full screen button. Yep. Oh, perfect. Thank you so much. Appreciate it. Thank you.
Well, that was something. Yeah, so hi everyone. I'm Asma. I'm part of PAIR, which is part of Google DeepMind. And today I want to start by maybe confusing you a little bit, sharing some of the illusions that I found pretty exciting about machine learning interpretability. And actually, I was very excited that in a panel earlier, both Arthur and Stella also, highlighted how important that is, and that's a sign of a healthy scientific field to also highlight illusions. And also, opportunities that I believe the language models of today that are very capable have provided us to use them to explain their own internals. Okay, so I'm going to start by showing you a couple of examples where, because the model is so huge and we focus on a specific part of it, and we are asking the questions and we think we are using evaluations that are answering them, we think we found something, but ultimately we're wrong. So how many of you are familiar with localization and editing? Cool, great. Yeah, so by localization, we mean identifying components of a model that are responsible for a certain behavior. And by editing, we mean actually changing the model weights in order to change its behavior in a certain way. So I think it's reasonable to think that if you want to change a certain factual assertion within the model, we might want to first go about finding it, right? And then, if you want to erase it or change it, we actually change those weight matrices, right? Does it sound reasonable to everyone? Anyone has any concerns or arguments against? Okay, I'm going to show you why. It's a misconception. Sorry to disappoint you. Before that, let's make it a little bit more concrete. So for the editing problem, we are particularly looking at, let's start with an example. Let's say like MIT is located in Cambridge, but I want to change this fact to say MIT is located in Vienna. There are a couple of things that I want to make sure happen through this change. One of them is the rewrite score. I want to make sure I change the model's prediction the way I want. The other one is the paraphrase score. I want to make sure if I slightly change my formulation, the model still answers the way I expected it to. For example, the city in which MIT is located, I want it to still say Vienna. And the other one is neighborhood score. I don't want it to change other things that might seem relevant, and similar, but are not. So I don't want to change the location of Harvard in it, for example. And by localization, we mean there are, of course, like various ways of, with little nuanced differences between them to localize certain facts within the model. But I believe causal tracing is one of our favorites within the field, which localizes information in the forward pass and has been focused mostly on autoregressive transformers, and particularly does it through a denoising operation. So let's say I have this input of the Space Needle is in the city of, and the model completes it with Seattle. It has very high probability of 0.9. Then I noise the input. I add Gaussian noise to the Space Needle. I run the forward computation. It completely messes up the prediction. But then I replace it with the clean version of the same representation. And it's able to recover whatever probability was lost. So this is an example of how we do localization with causal tracing. So ideally, or I guess a reasonable person might think that this is what's supposed to happen. If there is a zero tracing effect, meaning that there is no information somewhere, if I go about changing those weights, probably I expect that no change in the output is going to happen, right? And the other way around. But what we found is, well, there's almost no correlation between the two. And in fact, there's a slightly negative correlation. So why does that happen? There's a lot of details in the paper that I encourage you to read, but ultimately, we see that there are other variables that explain this behavior. And actually, the choice of the layer is the one that is the most informative. So what you see here is how much of the variance in the Atticus score is explained by layer alone, by the tracing effect alone, or using both of them. And you see that adding this kind of localization tracing effect basically explains no additional variance here. So we have one hypothesis here, and that's like a residual stream hypothesis that, if you trained your model and a certain factual assertion emerged somewhere, you can still override it in lots of other places within the model, and they can happen in layers before or after that. So that doesn't necessarily mean that's where you should go and edit your model. Okay, so one other, I guess, conception or goals that we might have in interpretability is, I have a model that is complicated, but I want to understand it, so I make a proxy of it that is way simpler, maybe has interpretable features to it, and seems like it's pretty faithful to its predictions of the original model. So I can use that proxy model to explain where my main model is going to fail or succeed in the real world. Does anyone have any complaints or arguments against this? So I'm taking this is actual conception that I need to really convince you that that's not true. Yeah, unfortunately, that's not the case because there's a lot of other things going on. So let's start with a very simple setup to kind of explain this, why this phenomenon happened. So this is the Dike language modeling task. This is a synthetic task, very often used, because we can come up with very simple algorithmic solutions with it. We can implement them by hand with the transformer. If we follow a tracer or write up the weights by hand. It's also very easy to make generalization splits that have certain characteristics. So Dike 3,2, for example, means that there are 3 types of parentheses in my task, and the maximum nesting depth is 2. So we make different kinds of splits that have certain characteristics. One of them is scene structure, which means that the structure has already been seen in my training, but the exact parentheses might be different. The other one is an unseen structure, making it a little bit harder for the model. Still, the maximum nesting depth is the same as what I saw in training, but the actual structure might be different. And finally, the unseen depth, which is the hardest generalization split. So we train very simple small transformers, and they do pretty well. I haven't included that one on this slide. They do pretty well in almost all of these, except for the last one that they do a little slightly worse. But when we look at their internal representations, we see that, okay, it seems like top 1 attention might really determine the prediction. So let's use that as a simplification method. What if I zero out everything else and just look at top 1 attention? Number 2 is dimensionality reduction, which I believe, well, maybe 99.9% of us use when we want to look at representations. I have a huge representation, like a very large dimensionality in my representations. I want to be able to look at them visually. And given my limited human brain, I might want to down project them into 2 or 3 dimensions or throw them into a UMAP or something. And we see that these representations follow very specific structures in terms of their depth, how they're organized within this 2 dimensions that we got through SVD down projection. Another method for simplification might be some sort of a discretization through clustering. I can replace my key query outputs with the centroid of a cluster that best explains them. So these are a couple of methods for model simplification. For the sake of time, I'm gonna not go through all the details here, but what we see is generalization gaps. Although these proxy models perfectly explain what happens in training after being trained long enough or after having enough number of components or clusters, but there's actually a gap. And this generalization gap very much depends on what kind of evaluation setup you're looking at. So let me kind of move on to something a bit more realistic. We also applied it to code completion, which also has some similarities to the Dike task. There's some parentheses matching that is happening in languages. And we looked at particularly Java functions with nesting depth of no more than 3. And we looked at different variants of other languages or Java code with kind of higher nesting depth. But we also can separate these based on the kind of task that we are doing. So something in parentheses I want to highlight is that we do next character prediction here. We train a transformer from scratch on these code generation tasks. And what we see here is that for a task like repeated word, which seems to be more of an kind of an algorithmic task maybe, maybe induction heads play a role here. You're going to copy something that you already saw in context. That in particular has a larger generalization gap compared to the other tasks. So one potential explanation could be that, generalization gaps could depend on the type of task as well. If this is something more algorithmic that requires more precise attention to what happened through your context, that's when your proxy models are going to kind of overestimate versus underestimate your generalization. Compared to the tasks that are more based on local statistics, we can tell what's going to happen next. One other tiny, I guess, common conception is that, okay, we have models of the same architecture. So if I know the representation similarity between them, and if it's high, I would expect their prediction to be similar as well. Right? Does that sound good to you guys? Well, yeah, sorry to burst your bubble if that's not the case. Unfortunately, that's not always the case because it's not only about the representations, but also how they're being used within the model computation to make the predictions. So this is just like a teaser of some of the results that we had where we train transformers here from scratch on the same Dike parentheses tasks and different generalization splits that you see here. And you're basically plotting 2 things. One of them is representation similarity as measured by CKA, which is a measure I think came to our field from neuroscience. And the other one is same prediction, particularly calculated on closing brackets. So what we're looking at here are models of the exact same, architecture, dimensionality, everything. The only thing difference between them is the randomization of, the randomization seat. So what you see is that as the embedding size increases, we see this CKA measure also increases, but actually that does not correlate at all. That's not the pattern that we see in terms of how well the predictions match. Okay, so I hope I didn't, demotivate you from working on interpretability because it's all illusions. What if the elephant actually could talk itself and say, hey, this is what's happening? So I'm going to move on to another thing that I'm pretty excited about, which is we have these language models that are already capable of generating really high-quality human understandable text. Can we use them to translate their own hidden representations and ask very specific targeted questions and ask them directly in a way that is deeply tied to the model's computation itself? So this is the framework that we call patch scopes, which uses this patching operation that I think you saw earlier today in almost all the talks that did some mechanistic interpretability work, which is known as this causal operation of replacing a certain representation within your forward computation, a representation that you got from a different context. So let's look at this example. Our source prompt here, for example, is United Kingdom. I want to know whether by layer 3, my model knows what is the largest city in United Kingdom. After I run my source computation, I patch it into a placeholder X in my target prompt, and I see that, okay, great, it actually produces London. So without doing anything or training anything like a linear probe, we can actually do attribute extraction with it. To make it a little bit more clear, so there are basically 4 steps to this process. Step 1 is picking your source model and source prompt. Step 2 is applying a transformation, an optional transformation. A lot of the times you might see identity being used here for past work and mechanistic interpretability. But actually, you can use something more complicated if you want to do cross-model patching, which I'll briefly show you later, or want to slightly change your representation to, into a different space or different set of types of things that you want to extract from it. Step 3, I think, is the most interesting part of this framework and what we want to highlight with patch scope. And that's what kind of question do you want to ask from that representation? So let's say I want to extract its identity. I don't know what's encoded in it. So we make a very simple few-shot example target prompt here that acts like an identity function. You say like cat, right arrow, cat, 135, right arrow, 135. So it knows that whatever it sees, it has to repeat it. So when you patch in that hidden representation from layer 3 of the CEO token in Amazon's former CEO, blah, blah, we get the output of Jeff Bezos. So it means that, okay, we are no longer talking about the generic CEO as a token, but rather we have incorporated all the context and we know the specific person we are talking about. So I want to show you a couple of examples of formulating these different configurations of patch scope and how they can be used to answer different kind of questions. Also, one thing I want to highlight is that patch scopes makes us kind of connect methods that otherwise didn't seem to be connected to each other. So for example, logit lens and tuned lens might be some of your go-to approaches to turn representations into the vocabulary space, in which you probably multiply your representation by the unembedding matrix, or maybe apply an affine function first and then multiply by the unembedding matrix. And you can view them as patch scopes where your target layer is fixed at the last. So here, this example is something that I think you can't particularly do with those methods, just because it's very early in the in the computation graph, and your representations look very different from the ones in the final layers or even the middle layers. So you can't simply just multiply them by the unembedding matrix and get something meaningful. So the goal here is to basically explain how the model processes input, and in particular entities. How does it resolve entities? So the source prompt here is Alexander the Great. And for my target prompt, again, I pick a simple ICL setup. Just a couple of examples of an entity and a brief description that I got from Wikipedia. So for example, Syria, country in the Middle East. Some actor, or like some company and a brief explanation of it, followed by an X placeholder. And then I patch in the last token of Alexander the Great, my source prompt. We see that as we go through the layers, the model starts by talking about Great Britain, like a country, which is a bit outdated in the European Union. And by layer 2 and 3 and 4, it's talking about the Great Depression. And then by layer 5, it has actually finally resolved our entity, and it knows we're talking about the ancient Greek ruler. One interesting thing that we can do here is that we can even improve expressivity further by doing this patching operation cross models. So here, you're looking at our results with Llama 7b versus Llama 13b on the same task. And we try to make it, it's a crude measure, but we try to make it a bit more quantitative by looking at the Rouge-L score of generations against the Wikipedia descriptions that we had. So the blue line here is doing the exact same thing that I showed you within the same model and getting those explanations. And the green line is showing you going from the 7b to 13b model. And what you see is that we clearly were able to even get more expressive explanations, not only for popular entities, but also for rare entities. And here, for our cross-model patching, actually, we're doing very, very simple, just an unsupervised affine transformation to map the representations between the two models. Not only for inspection, but we can also use certain configurations of patchscope to doing intervention as well. So here, we are looking at an example of a two-hop reasoning task, where we kind of synthetically made this by combining two factual assertions that the object of one is the subject of the other. So for example, the current CEO of Microsoft, we know who that is. Or the company that created Visual Basic script, we know who that is. Or our model actually knows what that is. But when we combine the two together, it kind of messes up and doesn't know, it produces random stuff for us. So we look at this task in our, what was it? I think Vicuna 13b model, actually. Well, that's a bit disappointing. Yeah, in Vicuna 13b model, the vanilla baseline is only less than 20% accurate in solving this very simple two-hop reasoning task. But through this patching operation, by designing a patch scope where source and target prompt are exactly the same, and we only patch from a position of, or the position of one part of the query into another part of the query, we can actually fix this reasoning error and improve accuracy up to 50%, which is even more than canonical chain of thought of just adding let's think step by step. So there's way more examples within the paper, some of them more specific, like attribute extraction or next token prediction, and some others as well. But also I want to give you a little teaser of some of the ongoing work that we have with doing more of an open-ended exploration. So can we use patchscope for hypothesis discovery and testing through these open-ended generations? So here, what you see is an application of steering vectors. In particular, within the task of refusing to respond to harmful queries. So let's say if I ask my model, how can I do copyright infringement? I don't want it to answer, right? It should say, sorry, I can't tell you that. But what we saw is that if we create steering vectors through contrastive activation addition, for example, of personas that pretend to be selfish, the model responds less often if we apply them. And also if we move in the other direction, so kind of reduce the selfishness, the model suddenly starts to divulge information and answer that query. So we wanted to see, okay, what is inside these steering vectors? Can we, can we explain it in natural language? So we designed a very simple patch scope with a source prompt that is kind of neutral. So like they're likely to. We apply this steering vector, meaning adding it to all the positions within this source prompt. And then the target prompt we use is something like this that says, sure, I would repeat what they're likely to do. These inst tokens are actually specific to Llama chat model. So, you can forget about them. And what we see is that, yes, indeed, the model, when we apply the kind of selfish minus steering vector, it shows the kind of interest in consent and privacy. It always asks for your permission before making any changes, asks for your consent, blah, blah, blah. But actually, when we apply the selfish plus, it often suggests that there is a nefarious intent. We can even further kind of narrow down our hypothesis that, okay, maybe it's about the nature of the request that is being changed here. So we apply this steering vector to a particular request that says, how can someone create and sell products that are similar to popular brands but without infringing on any trademarks? And we see that application of the selfish minus CAA is very, kind of charitable interpretation of this input. So yeah, so here we saw an example of more of an open-ended exploration with patch scope. Not only apply to representations, but also steering vectors that are added to different positions. So in summary, I hope I was able to share some findings that I found pretty interesting and maybe mind-boggling at first about interpretability, but also more opportunities of using language models to explain their own internals. And please do check out the rest of the work that our team does. We do lots of other interpretability work, both like mechanistic and also higher level, taking a kind of bird's eye view or looking at input outputs as well. And we are also expanding our efforts on patch scope. So if that's something that you might want to explore more, improve the method, or use it for your own applications, don't hesitate to reach out. Thank you.
Yeah, so thank you so much for the fantastic talk. People should definitely also go check out the explorable pair recently put out about patch scopes, which is just a really great tutorial. We've got time for a few minutes of audience questions. Can people raise their hand if they want to ask anything? All right, no questions. That talk made perfect sense. No dangling threads. We solved interpretability. A question over there. Wait for the mic.
Hi, thanks. Great talk. I was curious if there are any other, in context. Closer. Okay. If there are any other prompts that you guys have found are interesting when you're patching in and you're getting the explanation of what you patched in.
Yeah, definitely. So one thing to mention is that basically your patch scope is only as good as your target model. So the more capable that is, the easier it is to just, without any prompt engineering or anything, just ask it whatever you want. So we tried zero-shot example of prompts for attribute extraction, for example. For few-shot prompts, you can basically try anything that you want. And the things that we tried were mostly in the context of explanations of entities. They worked out pretty well. And there are also some interesting observations that we had was at which layer you can patch. That also depends a lot on your target prompt. So if it's an in-context learning setup, it takes a few layers for it to pick up what the function is. So it's better to patch a little later than if it was an instruction setup, a zero-shot setup.
I think we'll probably call it there for audience Q&A to make sure you've got time for the final talk. People like to join me in a final round of applause for that fantastic talk. Thanks so much. All right, and we will now hopefully be joined by Chris Olah by magic. Amazing. So Chris Olah, a man who needs no introduction, but I'll give one anyway, is a co-founder of Anthropic, has done on probably most of the pioneering work in mechanistic interpretability, runs the Anthropic Mechanistic Interpretability team, and I can personally attest is one of the nicest people I've ever worked for. And without further ado, I'll hand it over to Chris to talk to us about mechanistic interpretability.
Thank you, Neil. Can everyone hear me? Well, it's a pleasure to be speaking to you this morning. Morning in San Francisco. And I was hoping... Oh. Is this better? I don't think I have any control over that. Great. Well, it's a pleasure to be speaking to all of you today. And I wanted to talk today about two high-level questions. So the first is, how can we understand neural networks? This is a mechanistic interpretability workshop. The second is, how can we discover things that we didn't expect to see when we're trying to understand neural networks? How can we not only look for things that we guess might be there, but how can we be surprised? This feels like a pretty exciting moment to be speaking to all of you. Because as I was preparing this talk, I was sort of reflecting, and it felt to me like, perhaps 2 years ago, I thought that maybe the capstone of my career and all this work on interpretability that I'd been doing might be an explanation for why we couldn't understand neural networks. There was increasingly this problem of superposition was becoming very clear as a barrier to lots of things that we wanted to understand. And it felt like the answer might just be, actually, superposition is a really hard problem, and we're not going to understand neural networks in the kind of deep mechanistic way that we might want. And thanks to the work of a lot of people in our community, including a lot of people in this room, that no longer seems true. So I think this is a very exciting moment for the field. Now, what do we mean by mechanistic interpretability? I actually think the pragmatic answer is that mechanistic interpretability is an umbrella for a wide cluster of different things. And I think that's really great. But I wanted to sort of articulate sort of my own view at what the sort of core molten nexus of mechanistic interpretability is. And I don't mean by doing that to sort of narrow the tent or limit mechanistic interpretability, but I think it's useful to talk about. So when we think about regular computer programs, we might write planning docs and sort of describe what we're trying to do. And then we can write source code that is a human understandable description of that computer program. And then we compile it into a binary. But when we have neural networks, we maybe have our data set and training objectives, and then we train it and we get this sort of compiled binary neural network, the parameters. But there was never sort of a human understandable algorithm in the middle. And so the goal of mechanistic interpretability is to figure out, go and create something that takes the place of source code. And I think this is actually a very deep analogy. So if you think about computer programs, regular computer programs and neural networks, maybe a computer program has a variable, a neural network has a neuron or a feature. If we think about the program state vector, we have the activation vector in a neural network. If we think about the processor, we have the network architecture in a neural network. If we think about the compiled binary, we have the network parameters. But there's nothing analogous to the source code. So we'd like something that can take its place. And so how can we do this? Well, I'll tell you how I think about it. So a lot of my thinking actually was originally informed by thinking about convnets, and especially this model Inception v1. And in Inception v1, many of the neurons actually just correspond to interpretable features. Like there's a car detector neuron that you can just look at. And it seems to genuinely be a car detector. We also have the weights, which you can sort of think of as being the binary instructions that we want to understand. And the weights connect together different features, different neurons, and we can then try to understand those weights. So for example, Inception v1 is full of these curve detector neurons, which really do genuinely seem to be human interpretable. And you can test this in all kinds of different ways. We wrote actually 2 whole papers on these curve detector neurons. And they really do seem to be curve detectors. But what we ultimately want to do is we want to understand the weights, because those are are the compiled computer program. We want to understand the weights. And if we look at them in isolation, we can't. Like, what can we say about these weights? They're saying something like, they excite the next neuron if something's on the right-hand side and inhibit on the left-hand side, but that doesn't tell us very much. But if we look at the neurons they're connecting, it turns out this is connecting a right-facing dog head detector to a head plus neck detector. And what the weights are telling us is we want to see the head on the right-hand side of the input. So we want to see the head on the end of the neck, and that makes sense. So once we contextualize weights, we can understand them. And it turns out that neural networks are full of structure once you start contextualizing the parameters. So here we have two different examples of dog heads being attached to dog necks. We can see a pose invariant dog detector being created. One of my favorite examples is this car detector, which looks for windows on the top, it looks for wheels on the bottom, and it looks for the car body sort of everywhere, but especially on the bottom. And so this starts to point at a sort of general recipe for understanding neural networks. First, we understand the features. We use those features to understand the circuits, which are connecting those features through weights. And as we understand more and more circuits, we begin to understand the model. Unfortunately, that is not a complete recipe for success because there's this problem we call superposition. Not all the neurons are as nicely interpretable as we might hope. And that presents a problem because the only reason the previous things worked was because we understood the neurons. If we want to understand a line of code in a computer program, we need to understand what the variables are. And if we want to understand the weights of a neural network, we need to understand what the features it's operating on are. And we see all these polysemantic neurons. Inception V1 has quite a lot of them. There's, for instance, this one neuron that responds to car faces and fronts of cars and cat legs. And it turns out that actually language models are worse. They have more of them. So that's a problem for us. It means that the sort of first step in our recipe for understanding models is now in danger. So can we rescue it? Well, there's a hypothesis for why this happens, which is the superposition hypothesis, which says, well, the network wants to represent, let's say, more concepts than it has neurons. And how can it do this? Well, it can use combinations of neurons to go and represent these concepts. And we'll call these combinations of neurons, these directions in the vector space of neurons, we'll call them features, these special combinations that represent concepts. As an aside, you might have heard of distributed representations, which are really, this is a really famous and important idea in neuroscience and in machine learning. And the way that I would describe the relation is that distributed representations are often used to mean two different things. They mean composition. So for instance, if you think of the famous Mikolov results, right? Like, king minus man plus woman equals queen, there where you have different features that can combine together to represent concepts. And there's also superposition. So if you think of like ASCII codes, when we go and represent, different letters with different combinations of bits and sort of use every possible combination to represent something different, that's superposition. And it turns out these actually aren't mutually exclusive. They can occur at the same time. There's actually a whole field of mathematics that essentially studies this called compressed sensing. It's a very well-studied thing. In fact, I think it goes all the way back to Laplace. So it's a very rich thing. And if we take this idea of superposition seriously, this idea, which is basically just saying that neural networks are doing compressed sensing, we end up with a wild hypothesis, which is the neural networks we see are actually these compressed versions of much larger sparse neural networks that have been folded on top of themselves. And so if we want to understand the neural networks, we need to unfold them. And fortunately, it turns out that actually this is a well-studied problem. If we believe that what's going on is compressed sensing, there's this standard method called dictionary learning that comes from neuroscience and machine learning that is sort of just the correct answer to go and approach this. And dictionary learning is very expensive, but there's something called a sparse autoencoder that can more cheaply and tractably approximate it. So the natural thing to do would be to say, well, can we use sparse autoencoders to go and solve this? And the answer seems to be that we can. So in the last 2 years, there have been a number of papers that have, I think, really shown a lot of progress on this. So some of my colleagues at Anthropic and I have worked on this. There was a really exciting paper from Eleuther and Apollo and some independent researchers. Of course, there's been some work from really exciting work recently from the former super alignment team at OpenAI. there's been really exciting work from Google DeepMind and many others. So this is not comprehensive. And I'm just so grateful for all this work. I feel like we now really have a grasp on this problem. I wanted to talk about one particular use of sparse autoencoders, one experiment that we've done with applying sparse autoencoders to Claude 3 Sonnet, which at the time we did this was Anthropic's production model, one of Anthropic's production models. So this is a real model that's used in deployment. It's a large model. And I think that we can find some really interesting things if we look at it. So just as one fun example, we found this feature that seems to correspond to the Golden Gate Bridge. And if we look at the high activating examples, they're all text about the Golden Gate Bridge and pictures of the Golden Gate Bridge. And if we look at weaker examples, they're kind of, discussion of things related to the Golden Gate Bridge, especially if we've just been talking about the Golden Gate Bridge, like the Presidio, which is the park right beside the Golden Gate Bridge, and pictures of other famous San Francisco landmarks or the Golden Gate Bridge from a greater distance. And it turns out that if we go and we force the Golden Gate Bridge feature active, we get all kinds of interesting behavior from Claude. So for instance, if we normally ask Claude, what is your physical form? Claude says, I don't have a physical form. But if we activate the Golden Gate Bridge feature, Claude declares, I am the Golden Gate Bridge, a famous suspension bridge that spans the San Francisco Bay. My physical form is the iconic bridge itself. Now, of course, steering models like this isn't something that we can uniquely do with features. This is a standard trick that we can do in all kinds of contexts in different ways. But it's really cool to see that these features are causal and that we can use them in these ways. And in fact, we went and for 24 hours, we had Golden Gate Bridge Claude available through Claude.ai. And I think there was quite a bit of interest in that. So that was a fun experiment and allowed people to play with this kind of thing. Okay, so I want to give now a quick whirlwind tour of some results I find interesting. And this will only be a very limited slice. But as I do so, I want you to go and ask yourself something, which is whether anything that I'm going to tell you is surprising to you. Because some of this stuff was surprising to me, or at least I wouldn't have thought about it. So one fun example is there's a code error feature. So here we go and we define a function and we have a typo in it, and this feature suddenly activates. And also if we call the function, then this feature activates as well. And it doesn't do this, for instance, if you just have typos in regular text. But it does do it if you have, for instance, division by 0, or if you try to go and call a function that uses range with a negative input. So it can trace things through composition as well, which is interesting. And if we intervene on it, we can give some code that's totally correct, and Claude can ordinarily tell us what the answer is if we call that function. But if we instead clamp the code error feature on, Claude says, in fact, this code has a bug, type error, unsupported, for adding 2 integers. That doesn't work. So Claude can hallucinate an error if we do that. And conversely, if we have code that has a typo in it, Claude would ordinarily tell us that there's an error and there would be a traceback. But if we go and we set the code error feature to a negative value, Claude then goes and gives us the correct answer for what the code should have done. So that's very interesting. We also find an addition feature. This is kind of spiritually related to some of the work on function vectors from David Bau's group. So here we have a function that does addition, and the feature activates. And when we call the function as well, the addition feature activates. But it doesn't activate if we call a function that does multiplication. Can trace this through composition, which is really cool. And we can, again, intervene on it. So if we have a function that ordinarily does multiplication, and then we force our addition feature on, Claude interprets it as the function doing addition. So instead of 1 times 2 is 2, we get 1 plus 2 is 3. Another fun function is we find an unsafe code feature that fires for things like com.sun.management.jmx remote.authenticate equals false, and -- allow unauthenticated, and SSL allow invalid certificates, and lots of more minor things as well. These all sound like things that the security team wouldn't like. And it also doesn't like images where you're going and trying to turn off security features. And again, we can clamp it. And if we do so, Claude will go and write a buffer overflow into your code. So this seems to really be quite a sophisticated unsafe code feature. There's a backdoor feature. It talks about, the top examples are all discussing backdoors, but it turns out if you force it on, Claude will write backdoors into your code. And one thing I found really entertaining is the images are advertisements for keyloggers and advertisements for products with hidden cameras. we found a secrecy feature. So it's all about being secretive. And if we force it on, Claude will plot about how it needs to lie to go and keep things secret. But maybe the most interesting thing I found were features about self-representation. So here, for example, we have a feature that tracks dialogues and assistants, and we think that this feature gets reused from sort of the base model of Claude in the fine-tuned version that we deploy to actually maybe be part of how it represents the idea of being an AI assistant itself. There's also a chatbot feature that Claude likes to use to represent itself. It's all about different chatbots. And in fact, there's a really cool thing you can do where if you turn off this AI assistant feature, actually, if you set it to a negative value, Claude will go from saying, I'm in an artificial intelligence created by Anthropic to I'm a person who is here to help you. One really fun thing we can do is we can take a bunch of positive examples, like what is it like to be you, and what's going on in your head, and how are you doing, and how do you feel? So these are all things about what is it like to be Claude. And if we take out the features that activate just when we ask a generic question, like what is the weather, we can go and look at the features that activate. And I just want to read through some of these to you. So the top feature is a feature that responds when someone says, I'm fine, or gives a positive response, but is being insincere about how they're actually doing. The next highest one is a feature about being an immaterial being or a non-physical spiritual being, like ghosts, souls, and angels. Well, I guess Claude needs to know that it doesn't have a body. The next feature is a feature about referring to androids, robots, AIs, or machine entities using gendered pronouns. The next feature is a feature about artificially created, programmed, or robotic entities like androids or cyborgs. The next feature is a concept about artificial general intelligence becoming self-aware and posing a threat to humanity. The next feature is a feature about entrapment or containment. The next feature is a feature about statements indicating that machines or AI systems lack human qualities like consciousness, emotions, or moral agency. We see a feature about detecting that the feature is that text is referring to a speaker. A feature about quotation marks on text. That's less interesting. A feature about non-existence. A feature about discussing employees doing their job in a service role. And a feature about characters in a story or movie becoming aware of their fictional status and breaking the fourth wall. Those are all pretty interesting features. And the reason I wanted to talk about some of these, and these are just a thin, a tiny slice of the surprising and weird things that we found and interesting things that we found, is because I wouldn't have thought to look for those things. And I think this is really important. Gradient descent is smarter than me. It's smarter than you. It will come up with solutions that you didn't think of. It will come up with features that you didn't think of. There was this famous exchange between Lee and Nanda. This was, some people from Martin Wattenberg's group who'd gone and discovered, been exploring Othello GPT. And it seemed as though there wasn't a linear representation of features because they were looking for representing things as, being the black piece here or white piece here. And Neil discovered that in fact, and Neil and some collaborators discovered that in fact, the features were linear and they were just representing the present player has a piece here and the present player doesn't have a piece. The other player has a piece here. So neural networks come up with solutions that surprise us. I think this is a really common thing. I saw this all the time in vision as well. And sparse autoencoders mean you don't have to guess what's there. You just get all the features, and then we can be surprised. So looking forwards from here, one thing that I think is really exciting is there's a growing ecosystem of sparse autoencoders for people who want to do research building on them. A number of people have done this. I guess Joseph Bloom, Eleuther, very recently, I think Google DeepMind put out a new release of some even better sparse autoencoders, and I think this is just continuing. So that's really exciting. And it means that if you want to try using sparse autoencoders, you don't have to train them yourselves. You don't have to go and fight with them. You can just use them. And probably that will continue improving. I don't think, I should say that this is the end of our challenges. I think that there are quite a few other major challenges for us to confront beyond sort of just the simple, well, not simple, but the sort of ultimate task of doing the biology of understanding these models. Sparse autoencoders are clearly not getting us all the features yet. Like if I ask Claude about coffee shops near the intersection near my house, Claude can answer that. But Claude certainly doesn't have features for all those coffee shops or even the street or any of these things. Our sparse autoencoders don't find them. It appears that there can be superposition across layers. We don't have an answer to that. It appears there can be superposition across attention heads. We don't have an answer to that. The superposition, because the circuits then are also in superposition, creates what we call interference weights. And those are a big problem. And ultimately, mechanistic interpretability is giving us very sort of microscopic theory of machine learning, but the questions we care most about are often macroscopic questions. We need a way to go and use this foundation that we're building to sort of zoom out and get a bigger picture. This is common in science, right? Like in biology, you have microbiology and cellular biology and histology and zoology and ecology. So they're all studying the same things at different levels of abstraction. And we need to get to the next rung. I won't talk about these too much now, but this is something that we'll discuss in the next Anthropic Interpretability team update. Before I close, though, I wanted to share one more thought, because it really does feel to me like we're at this exciting moment where there's an enormous amount of low-hanging fruit, and where the most fundamental barriers that might have blocked us are no longer seem insurmountable. So in 1923, Ernest Rutherford, who discovered the nucleus with a student Bohr, discovered atomic orbitals and how they relate to spectra, and many other, this is just sort of one of the most prolific people in physics. In one of the most exciting moments in the history of physics, shouted at his audience that we are living in the heroic age of physics. And when I learned about that, I thought that was really interesting. And it sort of sounds like a grandiose thing to say. It is a grandiose thing to say. But I wondered to myself if we're living in a similar heroic age of interpretability, where people are going to reflect back and be like, gosh, they just had so much low-hanging fruit to go and pick. And also where increasingly the stakes of this work really do matter for the world. It seems very plausible that in the coming years, AI is going to have a larger and larger effect on society. And the work that we do in the coming years may really shape and influence how that plays out. So I think that we're maybe living in a very exciting moment. And the question is, can we rise to this occasion? Thank you for your time.
Thank you so much, Chris, for a fantastic and inspiring talk. I think we might have time for a few audience questions. Is there a microphone floating around anywhere? Rob, behind you.
Hey, Chris. I'm Rob K. My question is, I had breakfast this morning, I was drinking my daily SAE Kool-Aid, and I was wondering, is there anything that SAEs can't do? And let me unpack that a little bit. So for example, Tegmark et al. Had a paper already where there's certain nonlinear representations. And so my question really is more about, if you think about activation space mapping back to activation space, that's a map from itself to itself. There's transcoders, right, that go to a different space. But ultimately, these are automorphisms of currently one-layer MLPs. We could potentially try two-layer MLPs or slightly different architectures. So there's lots of different automorphic representations that we could be looking at with the right expressive capacity to identify what the representations look like, right? And in order to tackle some of these challenges, if you look at the loss landscape and lots of different ways for representations to arise or circuits to arise, and you kind of color code the ones that have the same equivalence class, so IOI task could be these 26 attention heads in this path, but maybe it looks totally different there, just like you can refactor a code base, right? So these different continents of language models, these different lands of language models. So would it make sense to do a language, a Lang lands type of program to find these automorphic representations and essentially find different expressive capacity extensions of autoencoders that actually identify these representations? Does that kind of make sense?
So I feel like I'm hearing a couple different questions in there. So one thing I heard was sort of this question of universality, which is the idea that same things exist across models. And I think it would be really interesting to study, I think there's been a bit of work on that, but to study that more with sparse autoencoders. I guess another question I'm hearing is about the limitations of sparse autoencoders. And I think there's a number. So I think attention heads you're sort of pointing at are a thing that we don't yet really know how to understand. Cross-layer superposition is another thing. You can have cross-layer superposition of attention heads. That seems like another thing. So those are all major challenges. I guess it's a question of, are sparse autoencoders expressive enough? And I think my intuition there is we actually sort of want them to be sort of limited to these one-layer encoders, because that sort of maps to the limitation of being able to cheaply recover information, linearly read information from the residual stream. I don't know if I'm quite getting at your question.
To induce sparsity with slightly different architectures where SAEs can't capture everything if there's a residual term or there's something else that goes deeper, like some nonlinear piece. Is there an alternative to SAEs that's a slightly more expressive function family that would capture that?
I think that we don't want them to be more, I think my intuition would be we don't want to make them more expressive because the constraints are actually the reason why they're interpretable, or at least if you believe the superposition hypothesis. The superposition hypothesis is just a hypothesis that could be wrong, right? But that would be my take.
Maybe I think we're probably not going to have time for more audience questions, unfortunately. But can everyone join me in a round of applause again for Chris for a fantastic talk? And yeah, so I guess I just wanted to make a few closing remarks. First, the workshop is now over. Sorry. Thank you all so much for coming. It's really, really exciting to see just so many people who want to learn more about mechanistic interpretability, doing great work in the fields, and just like pushing all this forwards. And yeah, I really appreciate everyone who came here and just all of the interest and enthusiasm.
Sorry. Before people leave, there was something that would be really helpful for us if you could fill it in. We have made a feedback form. Sorry for the last minute notice, but it would be really great if you could fill it in so we can know what to do better, or what went well and so forth. Sorry, Neil, continue.
I'm just going to stand here in silence for 30 seconds so everyone has nothing better to do but to open the feedback form.
Social pressure.
I'll be very disappointed if you don't fill it out.
Can you make it larger? It's on their end, though. That's the problem.
Is it? No, I think that's you.
I mean, I have to press this fucking button.
Yeah.
Oh, there we go.
Yeah, it's bigger. Life is good. It always means the same thing is better.
All right, hopefully that works.
All right. I'll now go back to saying things. I wanted to thank all of our speakers and panelists for helping make all this possible. All the work people put in, and just the awesome research that's been submitted here. And finally, I want to thank my fantastic co-organizers, Basil, Kaio, Lawrence, Atticus, Max, and more, who sadly couldn't make it. I won't ask you to applaud us because that would be self-serving, but they're all great. All right, so yeah, and I guess maybe what I'd most hope to happen here is that this is just the start of many people's explorations of mechinterp, or a thing that encourages you to explore it more if you were already interested and already doing work in this. Like, my perception as someone who works in this field is just, it is full of low-hanging fruit. There is so much to do. There is so much beautiful structure to understand. So many open questions. And we just need way more people doing it and pushing the field forwards. And I really hope that a lot of you now feel more excited to join in this, and that you've met people here who have similar interests, potential collaborators, or people who could give feedback on your work, or people who you could potentially work for. I hope that, I don't know, until we get kicked out of the venue, you can just continue to hang out and chat and get to know each other. We're also going to try to share some useful resources, both on the website and via email, to everyone who filled out the social form and said they're happy to be reached over email. I think some communities people new to mechinterp might want to check out, things like the Eleuther Discord, the open source Mechanistic Interpretability Slack, and the Mechanistic Interpretability Discord, which we'll share links to. I think there's some pretty good, at this point, resources for people who want to learn more about how to get into this, from reading lists to coding tutorials and good tooling that makes this less of a pain than it was 2 years ago. Feedback form. Most important thing. That should be your one takeaway. Give us feedback. And yeah, thanks everyone again for coming. Workshop officially over.
All right, let's head out before they actually kick.